Welcome back, everyone. We'll give the rest of the class some chance to log in and get started in about 5 minutes here. All right, welcome back, everyone, to day 2 of our parallel computing training. Today we are going to be wrapping up some of the things that we had started yesterday. So if you'll remember, we were right in the thick of learning how to use multi-threading safely. And so we'll come back to that, wrap up that course, talk a little bit about parallel algorithm design and ways in which we can think in parallel. Then we'll dive into the two big beefy portions of today's training, which are distributed compute and GPU compute. And for the last one, we'll be logging into a secret version of our in development Julia Hub. And so that should be a lot of fun towards the end of the day today. That's why I'd asked you all for your email addresses that you've logged into. We should have just about everyone signed up there. Amit, I just need a email address from you. So if you could send that to me privately, I'll send that into the dev team and then we'll be in good shape. Okay, let's just start off again. I kind of like starting a little bit, gently in the morning for those of you, especially if you're towards the western coast of the United States. This is an early morning for you all, and so yes, thanks, mate. So that like to start off a little bit slowly. Let's recap what we looked at yesterday and talk about where we're going today. So if you remember, we started off the day with a really deep dive into high performance Julia code. And that's important because that's that base level that we're going to try to multiply by moving to parallel. Then we moved to single instruction, multiple data. That is still just a single core, right? But the ability to express our algorithms in a way that we can use single instruction, multiple data is a huge benefit and can be as big of a 16x speed up right out of the box without you even doing anything magical, just being a little bit careful about, for example, using @inbounds macros to make sure you don't have a bounds check block, because that'll block this from happening. And the that's kind of the little things like that to make sure. Yes, so we talked about this. We talked about the kinds of speedups you can see, how it's a fixed bit width. And so there's some cases where using lower precision numbers, so float 32s instead of float 64s, can give you a full 2x speedup, which is pretty cool. And we'll see more of that towards the end of today. And yes, we talked about how you make this happen, right? Often it just happens automatically. You don't even need to do any annotations except for inbounds, right? That's the one thing, because if you have a bounds check in this for loop, well, it can no longer combine all these things together because there's going to be a branch and that can't be done in a single instruction, right? You need to check and throw an error, and it might happen in between. You might get a bounds error at x3, and so Julia will have expected you to have set x1 and x2, but not x4 if the bounds error happens at x3, and that can't happen in a single instruction. And so the inbounds macro is very important to get this happen. Really good for that tight numerical code, that hottest innermost loop of your code. And in some cases, the @SIMD macro can make that happen for you. So that is how SIMD works. Right now we're in the middle of multi-threading, right? And we've seen how this works, how the basics here, but we've not really learned how to use it safely yet, right? We're still puzzling out how to just add numbers up, which ironically is, while it's a simple task, it's actually a little bit more complicated than everyday workflows. And so I like it because it's simple to understand. And then it's easy to transition the learnings that we get from that simple task to your everyday workflows. And so that's why we do it this way. But that's where we are in the middle of this lecture. We'll talk a little bit about that. We've talked about how matrix multiplies are already multi-threaded, and then you can multi-thread your own code with this @threads macro. And then today we'll also talk a little bit about how Julia 1.3 introduced a new threading paradigm that is really awesome, that we've now made stable in Julia 1.5. So it's something you can lean on, and it's a robust mechanism for doing multi-threading. We'll talk about how that works. Ironically enough, not during the threading session, and there's a good reason for that, but we'll get to that later today. Then the meat of today will come from multi-process and GPU computation. So multi-process computation, or distributed computation, or cluster computation, all of these things are different ways of describing the same concept, where you have multiple machines interconnected with many independent Julia processes. And the mental model I like to have for this form of parallelism is like you're running around a computer lab like a madman, typing on every computer, dividing up your algorithms. That way, you have computer one on your left doing, the first quarter of your algorithm, this computer doing the second quarter, this computer doing the third quarter, and so on and so forth. And you're manually hacking away at the keyboards of all of these, computer lab machines, getting them started back in the days when there were computer labs. I don't know, do colleges even have computer labs anymore? Maybe maybe showing my age there a little bit. Oh, good. I'm glad to hear no people haven't gone entirely onto into laptops these days. So yeah, that's the mental model that I have for multi-process computation. We'll talk about how this works. We'll demystify this later today. I don't want to get too deep into the syntax here, but the last section today will be on GPUs, and this we'll come back to talk a little bit about how GPUs work at the beginning of that session, because they work very differently than what we're used to. So that points us on our trajectory for today. Let's dive back into where we were in VS Code. So if you'll recall, we're in our multi-threading session. I actually just left this up overnight, so that way we can come right back to where we were. We've made it through the first three notebooks, halfway through here, and then we'll get through the next 5 in this course today. So I want to move a little bit quickly to make sure that we get things going. Now, if you'll recall, we had this threaded sum where we first tried just doing, where are we here? We first tried just throwing an @threads in front of our for loop here. And that didn't work, right? We got an answer slowly, and we got the wrong answer. So the reason there was because we were reading from and writing to the same variable across lots of threads, right? And so these threads were in contention. It was a race condition. So we wanted to coalesce that read and the write into a single atomic operation, and an operation that can't be split apart, that Julia will synchronize for us in the back end very nicely. And so it's called an atomic operation. And the way you do that is just by saying, hey, let's create an atomic number that supports these kinds of atomic operations. And so you can see there's all these sorts of things that does, all the sorts of atomic additions that you would want. And other operations too. So you can multiply, divide, basic operations that you would expect to have are available to you here, and they're atomic in that they are, they're going to read and write simultaneously. And that worked, right? That gave us the correct answer, but it was really slow, right? And it was slower than even just doing the one core thing. And the reason is because they needed to, all our threads needed to check to see which core had the latest version of our number, grab it, update it, prevent all the other cores from grabbing and updating it while the current core is doing it. And so you end up serializing your process. And not only do you serialize your process that you had tried to parallelize, but as part of that serialization that's happening, you are slowing things down because you're needing communication overhead. So how could we do this, right? So there's overhead in synchronizing amongst atomics. And importantly, that overhead is huge compared to the amount of work that's required to add two numbers, right? So when we're doing our atomic addition here, that's the only thing that's happening inside this for loop. And the only real work that's happening is a plus, right? And that's going to happen on the order of a nanosecond. That's like a single computer instruction. So we need, that means that the overhead of communication just completely swamps the actual real work. And so we end up spending 99.9% of our time communicating about how we're going to do our work and 0.1% of the time actually doing the work that we want to do. And so that's why this is slow, right? That makes a lot of sense when you think about how this is happening. So how might we improve this? Well, here's an idea. What if we do two levels of split up, right? We do an outer for loop that just doesn't go over an entire data set, but just goes from 1 to the number of threads. So if you'll recall on my computer, this will just go from 1 through 6, right? And we're using at threads to split it apart and say, we're going to divide up the iteration space here, this 1 through 6. We'll divide it up amongst our 6 cores evenly, and have all 6 of those cores run this portion, this inside section simultaneously. And because there's only one iteration per thread, it's pretty straightforward for us to reason about how this works, right? So that means that all these 5 lines of code, 6 lines of code here, are going to run simultaneously. We'll kind of split apart at the line 128 here. We'll split into 6 threads, and all 6 of them will execute this simultaneously, which means that instead of all 6 of them referencing the same the same result bucket, they now each have their own independent local thread. You can think of this as a thread local variable that is only going to apply to that particular thread. Well, if this R sub t here, remember you can type this, and if you're curious about how you type it, just ask for help, copy and paste it. We'll say that we don't have documentation for it, but we'll tell you how to type it, right? So this R sub t here is just what I'm calling the thread local version of our result bucket. And we'll automatically get 6 of them because we're dividing our iteration space across all 6 of our cores. And so that means that we can then have an inner for loop that loops over just a subset of our array. Now, this is where things get a little bit messy, right? Where we need to automatically and dynamically do a little bit of math to figure out which subset we're talking about. And so there's just a cute little idiom here that you can play with. There's a lot of ways of doing this, but you can use what's called divrem to divide and get the remainder of how many threads and the length. So this means that you can split our array. Remember that our length array is, 10 million values? Selecting groups of 3, yeah, 10 million values. And we got this by getting A as being, if I hover over it, it'll tell me where I defined it. Oh, I guess it doesn't. A as being a rand with 10 million values, right? So if you're coming back into this from a cold session, that's how we got that. So that means that you can divide this up into 6 chunks of 1.6 million. And if you multiply that by 6 chunks, you get almost all 10,000 of our elements. You're missing 4 though, right? And so that's what the remainder tells you, is how many elements you're missing. So this, div rem can be nice to get the length per chunk and the remainder kind of thing. So then we just need to be a little bit smart about, which chunk we're working on, and you can do a little bit of range computation here. So say if we're in the second thread, for example, this will be the bunch of indices that will add that second thread will add together for us. You can see it's the, from 1.6 million elements to 3.3 million elements. All of those elements will be added together with a separate for loop here. And of course, we can then use SIMD, right? We know how to make the fast, make the best use out of this one core with SIMD and an inbounds annotation. And then we can just use this single bucket, right? And then once we're done adding all of those, 1.67 million values together from this given thread, well, then we can just do our atomic addition between our 6 threads, or however many threads there are, right? This is totally generic, but however many threads there are, this is the point at which we can serialize, right? And so then the overhead of our atomics here is going to be absolutely minuscule compared to the real work of adding 1.6 million values. And then in comparison, we're just doing 6 slow atomic additions that need to serialize or sequence or coordinate. Doesn't matter how it does it. Julia will take care of that for us, and we can do it. Of course, then the real annoying part is that this for loop here only handles those first, where is it? The first 9.9999 million values, and we have 4 values left over. So you need to generically write another for loop that'll add those last values together for you. And of course, this could be as simple as using the built-in sum function. That kind of feels like cheating, though, if we're implementing sum. Same thing here, right? We could actually have this written as the built-in sum function, right? And just have the built-in sum function take care of this for us. Again, feels like cheating. Gotta, we're implementing our own threaded sum thing. Let's not lean on the built-in stuff, but this could be a lot simpler, is my point. The reason I'm doing this verbosely is just as a learning tool as we iteratively improve our multi-threading chops. So let's define this. We can send that to the REPL and run it and time it and see what we get. We do indeed get 5 million, and we get a fast value, right? We get something that was completed quickly. It took, on the order of 3 milliseconds here. And if I were to time, how long does it take for sum itself to do this? It's on the order of 6 milliseconds. So we're getting a nice 2x speed up. You might ask, why not a 6x speed up here, right? We're doing this on 6 cores. We have 6 threads, right? If you look at n threads, why aren't we seeing a full 6x speed up? And the answer here on this particular case has to do with memory bandwidth. There's a limit on how rapidly we can move 10 million values from our memory to our computer, moving all of those data all around our computer. There's a limit there, and that's what's called the memory bandwidth, and we're saturating that. So that means that we're working our processor as fast as the data can get to it, essentially. And so, sure, this is, it's a nice speed up here. And in many cases, you're not going to be seeking through, this much data. You're going to be working more on repeated computation, but memory bandwidth is something to look out for. Not much you can do about it, but it is, it's a kind of the hard limit of how fast you can do that. The one thing you can do is work on, making your algorithm use the memory more efficiently. And so actually, I think this might work a little bit better if instead of splitting this up into 1.6 million chunks, and I take each chunk separately, I think I might get slightly better performance if I were to take every first element, every second element, every third element, or I'm sorry, 1 out of every 6 elements, 2 out of every 6 elements, 3 out of every 6 elements, and get 3 mod 6, 4 mod 6, all the way down, because then all of my cores are working on the same view of the matrix of the array, and they should be able to get a slightly better performance that way. It's instead of needing to gather all the memory together, that's slightly more cache friendly is the words that we use. That might be a fun experiment to do if we have time towards the end of the day today, to change this algorithm so that way instead of batching them like this, we stagger them and look at every 1 out of 6 elements. So it's like if I only had 2 threads, you'd grab all the evens and all the odds. If I had 4 threads, you'd grab all the evens, odds, evens, odds, and so on and so forth. All right, so that's where we are. We got something that's faster than single core performance. We're nicely multi-threading. We're actually using our cores, but it's complicated, right? It was kind of a pain to write. There's also a problem where, one of the lovely things about Julia is its generic computation, where you can define your own data structures or extend things to data structures that can be, a very powerful mechanism. You can add units to data, you can add measurement errors, you can do all sorts of fun things. This algorithm won't work with any of those fancy types. It won't even work with complex numbers, right? And it'll say, because atomics need to be supported by the processor. They're a very, very limited set of types here. You can see basically just the built-in floating point and integer types are supported in atomics. And so because we're using atomics to synchronize, it's not going to work for complex numbers. So isn't there an easier way? How can we do this in a simpler way that gets us the performance we want with a nice ergonomics of being able to use Julia? And of course there is. We want to do this, and kind of the trick, this is a very, very, very common trick that I encourage you all to use liberally and throughout your code, is to have a result vector. So instead of using a single value for my results, or instead of manually creating thread local variables that I've then atomically synchronize, well, I could just create an array, right? Julia is great at using arrays. I can create an array of all the zeros that I need, all of these result buckets, right? Remember, I started with a single result bucket, adding them in. Well, if I just create an array that's n threads long, then I could say, hey, this element is going to be my first element for my first thread. This element is going to be for my second thread. And then this is kind of like Scratch workspace for all of my threads to have their own sequestered independent things that they can work on and do. And it's really easy for me as a programmer to work with it, because I can just iterate over all of the indices in my matrix. So with this fourth definition here, I can just iterate over all the indices, let threads divide that up however it best makes sense to do. I don't care how the threads macro does this. It can do it whatever way works best. It's just going to give me a bunch of indices that are split amongst threads. And then this intersection here, well, this will run on one of my 6 threads. And of course, then I can index into my results array by that thread's index to give me its own workspace, right? And so if I'm on thread 1, the value that I'm going to work on here is r sub 1. And I just, use the plus equals like we had been done. It'll read from and write to this variable, but because it's only r at the given thread ID, that's going to be the only thread that'll touch this. And so there's no longer a race condition, no longer a problem here. And then all we need to do is sum all the values in R in order to do it. Again, I did this in a for loop, but really, I mean, this is kind of silly to do here, right? I mean, really we know how to add 6 elements in Julia, and the best way is to just return sum of R here, right? Like that's that's what we're doing. The for loop here is, again, just because we're implementing sum. Doing this in terms of sum seems silly, but that's what we're doing. I'll comment that out and use as it was written, but this is the definition then, right? And so now we can time this, and sure enough, you'll see that we get about the same performance again, of about 0.3, 3 milliseconds or so. Again, bandwidth limited here on how we can do it, but we're getting the correct result. We're doing this right. It does lose the ability to tack on an @SIMD. So in some cases, if you're not memory bandwidth limited, you will see this being this convenient thing being a little bit slower. But in general, you're not going to be doing, your threaded loops often end up being on the outside of your program, right? Or a little bit farther away from the inner loop. The times at which you're multi-threading something as simple as a sum function are going to be fairly limited. And so that's just a small trade-off there. But that's the way this works, right? And it's pretty straightforward. So some key takeaways here on how this threaded sum works and the way that things are, we've done this. So you can protect your race conditions, right? I guess, all right, let me start with the first bullet point here, is that kind of the blessing and curse of multi-threading is that you have lots of execution processes, you can think of it, lots of, Julia's able to run different lines of code simultaneously, and they all have access to the same memory, right? They're all living in the same memory space. They all share the same data structures. And so they have this shared state across all their threads, which you need to be careful about, right? Anytime you have shared global state like that, it's kind of a tricky thing to work with as a programmer, and this may lead to wrong answers if you don't program them carefully. And so you can protect yourself. Like I showed you, using atomics is one way of doing that. That's kind of a way of explicitly synchronizing around a data structure. You can also separately synchronize things using what are called locks or mutexes. Those are also supported in Julia. I'm not going to demonstrate those to you, but they work very straightforwardly. And it's kind of the same concept as an atomic. It's explicitly telling the computer to synchronize around this thing. And if one thread has a lock that prevents any other thread from working with that lock until it's released and another thread can grab it. It's just another way of allowing Julia to do the synchronization for you instead of dividing up your algorithm in a way that you as a programmer need to do the synchronization. And so that is one way to protect yourself. But really, much better is to figure out how you can divide up your work so that way you just don't share state in the first part. And so one handy idiom is this, threads for I and 1 to n threads, and then having a result vector that, each thread has its own scratch space. And so that's how you can do this. And then using that array and accessing a single thread's elements is another way of doing it. And you can combine both of these idioms together really nicely and easily using that thread ID indexing trick and the result vector. This is how you can do this. So you can explicitly structure your multi-threading in many different ways. It's very flexible in this manner. So this brings me to a few warnings here, a few things that you may want to look out for. One of them is indeed this global state, right? We're sharing execution, and so we want to watch out for any shared state. And global state is a especially pernicious form of shared state. So let's bring in benchmark tools again. And let's use a slightly more complicated example here, a good example that's great for parallelization because it, all of our for loops are independent, is that of a Monte Carlo simulation. And a Monte Carlo simulation is just, you grab some random numbers, you do some test with them, and then you get a result. And so this particular example is doing the throwing darts at a dartboard kind of thing, where you ask, did the dart land inside a circle or inside a square? And if it, then you can compare the number of darts that landed inside a circle versus those that landed inside a square as a proxy for the area of each. A little bit of clever arithmetic can get you the value of pi. So this is just a very cute little way of computing pi, right? You can throw, say, 100,000 darts at your dartboard and get an estimate, 3.1415. That's about as far as I have pi memorized, 159, I think. So we're good to 4 digits there with 100,000 throws. I could do 1 billion throws here, 100 million throws, I should say. I could do 1 billion throws, and it'll take about 8 seconds to do, right? It's going to take quite some time, but I'll get higher accuracy because I have more darts that I'm throwing. So now I have 3.1415. You can get higher accuracy by throwing more darts. It's a terrible way of computing pi, but a great example of a class of algorithms that Julia is great for, right? Monte Carlo simulations are awesome in Julia because our for loops are fast. And so you can just express these very, very simply to say, I have n iterations of a for loop here, and all of my inside portions are independent, right? I'm just grabbing 2 random numbers and doing a test and adding into a bucket. Well, we know how to deal with that if we want to multi-thread this, right? By default, this is single threaded. So we're just using 1 core, but we could do this on multiple cores. We would just have to be careful about, race conditions adding to our bucket of how many darts landed inside that circle. That's easy enough, right? So let's use those same techniques that we learned to make this a fast multi-threaded implementation. We'll use the exact same thing we converged on for our sum example, right? Where we'll use threads for 1 through the number of steps that we have here, 1 through n. Allow the built-in threads macro here to automatically divide up our algorithm into however many chunks we have, how many cores we have. And then we'll of course use that trick of having a vector of results to count up how many landed inside for a given core, and the threads themselves will tell Julia which scratch space to work with, so there's no race condition. So we can do that and run this, and we'll get something that is slower than what we started with. So once again, we have done a naive thing here that sure seems like it should work, but we ended up with something that is slower. And as always, when you're moving with multi-threading implementations, when you do something and try to move to multi-threading and it ends up getting slower, you should look for places of shared state where Julia needs to synchronize. And if you think about this Monte Carlo algorithm, we're getting 2 random numbers here, and these random number generation, well, how does that work? It's not really a true random number. It's an algorithm that we're running within Julia. And, do this for, we'll have these, these are sequential random number generators. So when I get a random number, I need to increment some global that says, hey, we're going to give me a new random number at this point, right? And that global needs to be synchronized across all my threads. So here is a case where this rand function really, I think ideally, if we were being true to the Julia conventions here, really should be rand bang, where you're passing in some global RNG, and we're mutating, updating the global RNG. And so this would be kind of the explicit way of talking about this. We don't do that just because RAND is such a common function. But you need to be aware that, hey, this is doing some sort of global mutation to get to our next sequential random number. So that's why it's slow. You can actually inspect this. And in Julia 1.3 and before, you would actually get repeated random numbers with multi-threading becoming stable. I believe now we've fixed that issue, so you no longer get repeated random numbers. But that's, again, you need to serialize and make sure that your accesses to this random number generator don't mess them up. And so while the random number generator is thread safe, it's slow because of that coordination work. And so this section here, let's see, I think this will end up being, using random. I think this will, shucks, didn't grab the entire thing. I think, it is false. Okay, so it is still giving us different answers. So if you run this section, this block of code, you'll see that we're actually getting different random numbers in our serial version as compared to our threaded version. And I think, yeah, it's something to be worked on. This is no longer true. I needed to update this. I'm sorry. This is actually so it is thread safe, but it needs to coordinate amongst these things. Oh, interesting. So you're getting, so some of you are seeing that you end up with the same set of random numbers. I wonder why I'm not. I think it might just be because of the way that the threaded implementation works. It is thread safe, but sometimes you'll get slightly different answers. So how do we do this? We can explicitly use we can explicitly get this, and actually, shoot, I grabbed the wrong version of these notebooks. I have a newer version here. Shucks, I'm sorry. This is out of date because now we just have a random dot. Let's see here. Sorry about this. Yeah. So the key here, so this is on Julia 1.3 and before, you need to manually set up a bunch of different random number generators. So this is Julia 1.3. I'm going to change this. 1.5, we have random dot. So this sets up a bunch of independent random number generators that can, it uses the same trick where we have a vector of n threads and each thread gets its own random number generator that it can happily use and mutate and update, and it's its own workspace, and sets this up for us. We've taken this idiom and moved it into the standard library. And so now in the random toolbox, so if we just look at random.thread RNGs is kind of the magic. So it's using the random standard library. And then random.thread RNGs gives you a 6 element or however many elements as you have n threads. It's already set up to use exactly the idioms that we've been talking about, where you can go in and grab out your random number generator. And so instead of using what we did manually here, all we need to do is update this to use the built-in version. This also does a little bit more careful initiation of our threaded RNGs to make sure that we don't generate, that we're getting things correctly. Now, the tricky part here is that, we want to hoist this out. There's still a little bit of a performance snag if we did this inside our for loop directly. So you can do this, yourself and grab your threaded pie. This is, again, using all those same techniques that we've talked about, right? Where we're just doing one-to-n threads. We pull out our random number generator for the given thread. I could add that little subscript sub t like I had done before, because this is going to be a thread local. This v is also going to be thread local, right? Because it's not referenced outside of the for loop. That's how you know that it's going to be thread local. And so then all of the things in here are split amongst my threads. The random number generation, we explicitly pass in which random number generator is going to get mutated and updated, and we're pulling numbers from. And then we can get a much, much faster implementation that gives you the answers that you would want. And so here you can see that we have, oh, oops, I need to use a multiple of 6. Because I have 6 cores. So you can see here that we actually get a really nice, and in this case, it's almost exactly 6-fold speed up, right? If you'll remember, it took me about 800 milliseconds before, and now it's taking me, about 100 milliseconds or so. And so you get a really, really nice threaded speed up on this, and getting them working. So that is a little caveat emptor with random number generation, because Monte Carlo examples feel very, very trivially parallelizable, and indeed they are, but in multi-threading, you just have to be careful about the threaded state of your RNG. Okay. So a good question from Furtak asking, if we didn't know that random number generation was causing the slowdown, is there a good way to discover that? The answer there would be, I would profile, right? And by profiling, you would end up seeing that a lot of time is spent inside the random number generation, and more time is spent there than in the single threaded version. And that would be kind of your red flag to look out for. It's a good question. It's also just something to think about with your own data structures. You think about where mutation happens. Mutation is a problem, and so that's where you end up having problems. You can always access values freely from all your threads. It's changing them that can be a problem, and so the change of a value, so changing, incrementing to our next number in our random number stream is where the problem comes from, and that should pop up in a profiling trace. You'd see that you're spending all your time in the random numbers. So that would be the way that I would do that. There's also another question earlier from Dylan about, we keep throwing inbounds in front of all of our algorithms here. Why, is there a place where you wouldn't want to do that? So let me go back up here. So this threaded pie example, right? Why, is there any area where you wouldn't want to add an inbounds or, get these set up? And yes, there is, when you're initially developing your algorithms, never use inbounds, because if you go out of bounds, it can just crash your program, lead to memory corruption, do all sorts of crazy things. It kind of puts you in this unsafe land that you can really blow things up pretty quickly if your index ever goes outside of the valid range of indices. And where I've been using inbounds has been in cases like this, right, where I've allocated a vector that's n threads long and I index in with thread ID. That I know as a programmer will always be valid. My thread ID will always be between 1 and n threads. My number of indices here will always be between 1 and n threads. And so I as a programmer can tell Julia, hey, let's turn off bounds checking here, because I know that this will always be in bounds, so we can save that overhead. if you're ever not sure or doing some sort of fancy indexing computation, or doing some sort of, like, let's go back up here, some sort of crazy thing where you're doing a computation like this, where you're picking out which values to use, don't use inbounds here when you first develop this algorithm, because chances are you got this wrong the first time you did it, because it's an annoying computation to do, or some computation like this, right? And that's why I encourage you not to use computations like this, but to lean on other idioms to have the base library automatically split things up for you. So this is, one of those situations. So yes, don't use inbounds here, at least not first, until you're certain that this index will never go out of bounds, and then you can add in inbounds for it for your speed later on. I guess that brings me to a new thing in Julia 1.5 that I need to update the materials here for, is that we have this really nice tool called iterators.partition, where you can partition, say, the indices 1 through 10 million 6 ways. And it automatically will do that fancy computation that we had talked about. Or I guess, yeah, I always forget. I always do this backwards. So 10 million div 6. So this will do exactly what we had talked about before. This is new in Julia 1.5. And can split apart iteration spaces across your number of threads. So let's change this to n threads like this. And let's just collect all of these guys. And the beautiful thing here is that it will automatically split up your iteration space and deal with stragglers, do all of the fancy, crazy indexing that you need to do in order to get the values that you want. And it does this very, very efficiently. And so then, instead of worrying about any of these niggling indexing issues, just use iterators.partition to partition your data set into the number of threads that you want. You'll get 6 large chunks, and then one last thread will go and grab the 4 stragglers. And that allows you to do make these sorts of algorithms much, much simpler. This hadn't been efficient on Julia 1.4 and before. This is one of the reasons why Julia 1.5 is such a great release. But this was an awesome idiom to use, and we should incorporate this into our training materials. Sorry, I forgot about that little trick. Okay, then a few more little things to look out for in our last minutes of our hour here. The one is what's called oversubscription. We talked a little bit about this at the end of the day yesterday, how you sometimes want to have more threads than there is computation if you're waiting on user input or something like that. If you're doing something fancy like a matrix multiplication, well then, remember, our matrix multiplications are already threaded, and Julia, if you're using a threads loop, that's also multi-threaded. And so then this will, by default here, if we just run this, oops, what did I do wrong here? Oh, I'm running the wrong section. Okay. So, yes, sorry, I need to stop scrolling around so much. So BLAS is multi-threaded by default, and Julia is multi-threaded, or can be multi-threaded. And they actually currently use 2 different multi-threading paradigms, which is a little unfortunate. We're working on bringing those things together. This is only going to apply to matrix multiplication and other BLAS tools. But if you're leaning on a matrix multiplication in the core section of your algorithm, remember that this ostensibly serial matrix multiplication is actually going to be matrix, doing it's actually going to be multi-threaded in BLAS because the matrix multiplication is multi-threaded. And so that is multi-threaded in serial. If we explicitly told BLAS to use the same number of threads as Julia and did this again, in some systems, you may actually see a significant slowdown. On mine here, it doesn't look like I did see that. It really just kind of depends on, this is a little bit of a quirk of what your system looks like. We didn't actually see a speed up here. Might have slowed down just a little bit because now we're oversubscribing. And so then if we set our number of threads in our BLAS system to 1 and now run our threaded matmul, now you can see a speed up with using our Julia code. And if I did the same thing with now serial, it'll be slower because our BLAS is no longer multi-threaded, but Julia is. And so this is a little bit of a tricky little thing to look out for. But again, it's going to be if at the core of your multi-threaded algorithm, you're leaning on lots of matrix multiplications or things along that line, you'll just want to use only one of these two multi-threading paradigms. Either lean on BLAS completely or turn off BLAS's multi-threading and lean on Julia completely. Either is fine and you'll get the same sorts of performance either way. But that's how that is set up. And BLAS, that stands for the basic linear algebra subsystem, if I remember right. It's just the implementation of matrix multiplications and those kinds of array algebras, linear solves, things like that. It's one of the very, very few pieces of Julia that's not written in Julia itself. And the reason for that is because these libraries have been around for the last 4 decades and have been tuned and hyper optimized for specific computer architectures. And so every time a new chip comes out, the new version of BLAS comes out that has exactly the right structure to exploit the caching and all of the tips and tricks of that particular processor, the SIMD lanes, making all of these things as fast as possible. And it's, we use and can use the same BLAS that MATLAB uses, that NumPy uses, all of our modern compute ecosystem kind of has converged on this as the solution. And so that's what BLAS is. All right. The last section here is, remember, is this really, really annoying little piece of thing about modern memory and modern computer architectures that can actually sometimes bite you and be hard to identify where slowdowns are coming from. And it's called false sharing. So remember, the way in which, we had talked about getting our, dividing up our scratch space into a vector, right? Where each thread has its own index in that vector as being, this is my scratch space, this is where I'm going to work, this is, my safe haven for how these things work. There's one little implementation detail of how modern machines work that makes that a little bit of a challenge. So remember our memory latency table here where, as a programmer, we think of things as living in main memory, right? They have a single address. There's like a single memory location for our data. It'll get moved to our processor. We'll work with it and update it in main memory. That's the canonical location for it. This is all Julia objects live in memory. They only have one location, right? There's only one source of truth for this memory object. If you have an array, that is the array, right? There's no extra copies of the array. Under the hood, though, where we think about it, where our mental model is really far away from where the work happens, right? At this, scaled latency of 4 minutes versus the 1 second latency, or 100 nanoseconds versus less than 1 nanosecond. This distance is really big, right? And so in order to kind of bridge that gap, our modern processors have these caches here that make copies of our data to bring them closer to our processors. And so what our processors look like here is something like this, where, this is a somewhat old Intel chip from about 7 years ago. So they've actually gotten more complicated since then, but the same concepts apply. Where, here, this is a 4-core chip. You can see the 4 cores nicely segregated out here. And here is our memory controller that connects out to our RAM somewhere else on the motherboard. Remember, that's far away, especially in terms of the speed of light. And so this is going to take some time to access. So copies of your memory get propagated through into what is called the shared level 3 cache amongst all your 4 cores. And then inside the cores, there's a level 2 cache and a level 1 cache that brings the data even closer to your compute units. So that way, often the shared level 3 cache is on the order of 1 megabyte to 10 megabytes or so. Inside each core, these level 2 and level 1 caches are significantly smaller. And they just, essentially, it's kind of like your desk workspace, right? It's the things that you've been working on that you can reference quickly and easily. So if I have some data structure that I'm working with, and say I do that idiom where I have my my array of 6 elements, and I'm updating the first element as my first core here. My second core is updating the second element. My third core is updating my third element. My fourth is updating the fourth element. They all want to be working with data that's relatively close together. And the annoying little niggle here is that our computers, because they work with lots of data, right? Many gigabytes of data, many megabytes of data, they don't address things in single byte chunks or even 8-byte chunks. And so when you move data from your main memory to one of these shared caches to inside your core and things like that, you're actually moving what's called a cache line of data all at once. And this is often on the order of 64 bytes. So think about what's happening here, right? If core 1 is updating element 1 in my array, core 2 is updating element 2 in my array, core 3 is updating element 3 in my array. Remember, they're working with these local copies in these level 1 caches that then need to get written out to my level 3 cache, that then needs to get written out to my main memory at some point and synchronized, all behind the scenes, all without me as a programmer ever knowing about it, because this is supposed to be a totally seamless optimization that we as programmers never need to worry about, except in this one case here, where if I'm accessing sequential elements that are less than 64 bytes apart, well, this one updates that first byte in its 64 byte chunk. This one updates that second byte in its 64 byte chunk. And then they both go back to write that 64 byte chunk out to your level 3 cache. Well, they both now have 2 different versions of it. And so this is what's called false sharing. It's not true shared state, because we as programmers thought we were doing the smart thing, right? We thought that we were being smart about how we programmed, we segregated our data structure in a way that we can do this. And so a little bit of a diagram of how this looks like, right? Core 0 is working with element 0, core 1 is working with element 1. And they're both in a shared cache line that must get synchronized at some point. And again, so this is supposed to be an invisible abstraction, and indeed it is. The computers won't do something wrong here. Instead, you pay a price in time, because these computers need to work together to say, hey, I have a dirty copy of my cache line. You need to update it. I need to update mine. I need to write out the canonical version. Then you update yours, and all of this meta communication about how you synchronize all these things together. That slows things down, and can slow things down on the order of 5 to 10-fold. So that's annoying, right? And it's one of these things where I wish we wouldn't, as modern programmers, need to know about this. And this isn't something that's unique to Julia. It's just, when you're targeting highest performance possible, this is how our hardware works. And it kind of sucks and it's annoying. But the answer is pretty simple and straightforward. So the key thing here is to multiply by some spacing. And try to get this set up so that way you can space out your threads and allow you to do this. So I think this might work. We'll see if this works. Why did that work? Test. So here I created a very, very simple function that does some of the things that we had talked about, but now spaces our elements apart separately and allows me to check them out. Oops, I don't want to use semicolons there. I get rid of these semicolons. I'm hiding my benchmarking output. Okay, so while that's running, I'll talk a little bit about this. So why didn't we see this happen in our earlier examples, right? We saw speed ups. How was this? Well, the answer is Julia saved us from ourselves. In some cases, Julia is able to identify these cases of false sharing and avoid them. But here is an example where it's just barely complicated enough that we still haven't identified this to avoid the false sharing. And you can see that, with a purely contiguous spacing, so our zeros are just n threads long, so n threads times 1, and we're accessing them contiguously. Things take 23 milliseconds. If I space things out by 8 elements, then remember 64 bytes or 64 bits is our default element size for floating point numbers. So 8 times 8 is going to be 64, which is our cache line. And here you can see that we got a huge speed up now instead of a slowdown. It's annoying and frustrating that you all need to know about this, and I'm sorry about telling you this. I wish I didn't have to tell you this, but the key answer is that the idiom that I started off with of indexing into threads.threadid, that works most of the time, but the safe thing is to space out your elements so that way they're not contiguously arranged and you have spacing between them so that way they live on separate bus lines. And to go back to my cartoon, oh, I closed it. Why did I close that? To go back to my cartoon here, right? What's happening is now instead of them accessing the same cache line, they're accessing separate cache lines. So then we end up with this not going there, but rather hitting this element right here in a separate cache line. So that way these aren't shared anymore. And we've separated them out so that way, they can each work within their own cache lines and get things going. So do high-end processors avoid this problem? No, they actually make it worse because they have bigger caches, and they, the whole concept here is because the processors are trying to do something fancy, and we as programmers are seeing the price that's coming out. So that's the tricky thing, and it comes from the fact that we're sharing memory, right? That our threads share memory together, and so they can mutate the same memory structures. And if our threads didn't share memory, then we would be in good shape. We wouldn't need to worry about this kind of thing, and so that gets us to distributed computation, where we have multiple independent Julia processes, which avoids some of these problems. It introduces other problems, which we'll talk about, but it solves this entire class of problem. So that brings me to the end. I know it's kind of frustrating to come to a conclusion of a multi-threading thing where we've just gone through all the different ways in which things can go wrong. But really, it's not so horrible. Let me clear my annotations here. It's the key takeaways here is that you just use @threads, right? That's the key thing. But then we have to be careful about shared state. This affects both performance and correctness. You need to be aware of global state, right? Mutable global state, like we saw in random number generation. And in general, our built-in global states are, fully thread safe. This has now improved, and the built-in global state is fully thread safe. So this will just be performance. So that's where we see the performance impact. And then false sharing is also going to be a problem that you need to look out for. So these are kind of the three things to look out for. And false sharing is an even bigger problem if you have more than one processor chip. Because then not only do you need to share state amongst your single core, right? Each core has its shared L3 cache that we had talked about before. But now you have multiple L3 caches separated apart, and they need to talk to each other there. And so those are the kinds of things that you'll need to think about. In general, though, multi-threading is the best way to exploit the best performance out of a single machine. But we need to think about how we design parallel algorithms. And so with that, we're at the top of our hour. Let's take our 10-minute break, and then we'll come back and talk. I think I'll do an abridged version of our parallel algorithms design, so that way we can get into tasks pretty quickly and move to that and then get to distributed and GPUs. Cool. Great. Let's pull up our 10-minute timer. And I will see you all back here at 20 past the hour. Okay, welcome back, everyone. While we were away, we had a question about fonts and sometimes seeing black squares. If you ever see a black square in your Julia sessions when you're trying to use some Unicode character, the answer there is that you just don't have a font installed that can display it. And there's this really cool font called Julia Mono that was actually built by a member of the Julia community. Cormulian's his name. He's done lots of really amazing things, including, like, for example, the back of this t-shirt is designed by him. Lots of really fun things that he's done as a designer, and has designed this font that kind of gears for this. And so you can find more about Julia Mono. Let's see. Yeah, here we go. This is the link. And I think there are installation instructions here. All you need to do is just install it on your system. And then I believe almost all systems will use it as a fallback font. If you're using a different font and it doesn't have the character that you're trying to display, it'll display it in the fallback. This as a fallback. Or then you can also change the theme of VS Code. And I don't remember how to do that, but I'm sure you all can look that up and figure it out, you smart folks. So yeah, this is Julia Mono as a fun new font. Great. All right, let's dive into just a brief thing on parallel algorithm design. We're going to do this class quick so that way we can get to the meat of things. The idea here is just going to be to think about ways in which we can restructure our code so that way we can avoid some of the sharing issues that we had seen, right? Some of the troubles that we had seen with multi-threading. The core thing that we're going to talk about here is called the scan operation, or the cumulative sum operation, right? We know how to do reductions, where you just reduce plus over 1 through 8. That's the same as saying sum, right? This is just kind of a verbose way of applying a binary operator across an array. It's the same thing as writing sum when you reduce a plus operation, for example. You can reduce, multiplication, of course. That's the same as doing a product. You can do this with fun things like with matrices. If you have a cleverly designed matrix, well, then the reductions actually compute Fibonacci numbers. And this is kind of a cute little thing about how matrix multiplication works. We don't need to get into that, but it's kind of cool. So that's reductions, right? That's something that we're very familiar with. That's what we worked with in our previous notebook, right? We were doing a sum reduction. We were reducing plus over an entire data set, figured out how to do that in the fastest way possible with multi-threading. But now, what about a slightly more complicated basic instruction where we do a prefix or a scan? And this is kind of the same idea, only we make it general, so that way it's kind of like we'll introduce a general form of this, and the idea is that we just create a vector the same length as our original vector, where the first element is the same as our first element of whatever our input was. The second element is the sum of the first 2 elements. The third element is the sum of the first 3 elements, and so on and so forth. So this is the idea behind prefix or scan or accumulate. Those are all 3 words that folks sometimes use for this operation, where you're doing some binary operation. It could be plus, it could be multiply, it could be any binary operation where you're just incrementally adding on the next value to whatever was before, and you end up with the array result back. So unlike a reduction where you just get a single value back, we're going to get an array result back. And we have this built into Julia with cumulative sum, right? So you can do cum sum of, say, 1 through 8 here, right? And that will give me the numbers 1 through 8. 1, 3, 6, 10 is just adding, all of the numbers sequentially and giving me a vector back. So that's the cumulative sum. We also have the cumulative product, right? And these are going to be my my factorial numbers, right? Or the 1 bang, 2 bang, 3 bang, 4 bang, so on and so forth. And this is used for combinatorics and such. So we can write this, we can create our function that does this, right? And kind of a cute little trick that you can do with Julia is if you use one of these fancy Unicode operators like a circle plus, again, if you're curious about how you type this, just put it in the help and /o plus as an argument, you can actually use it as an infix thing here. So this could be plus, this could be star, this could be some other operation. Any binary operation can be used here. And it's just kind of a cute little way of using Julia and the Unicode capabilities of Julia to write this operation, right? And so this is how you would do this serially, right? You can have this serial operation that takes any value, right? And so we can do this prefix serial, with plus, and do 1, 2, 3, 4, 5 like this, and this will give me the same thing that's my cum sum. I could pass in star, and that'll be my cum prod. I can pass in any number here though, right? And it will, do that operation for me. Dividing will hit 0 really rapidly, so on and so forth. Lots of fun to be had here. But this really doesn't seem like you could parallelize this, right? Like this isn't really amenable to any of the parallelization techniques that we've talked about thus far, right? With multi-threading or SIMD, none of these ideas really work because we're updating the previous element and using that to kind of cache my operations, right? And going back to my sketch of how this works, right? We're taking our first element, then 1 plus 2, then 1 plus 2 plus 3. If I tried to do this independently, well, then I'm repeating computation, right? I'm repeating 1 plus 2 multiple times unless I reference y of 2, my new y of 2. And if I reference new y of 2, then I'm mutating my state. And it's a hard thing to think about, right? How do you multi-thread this program? It's not very obvious because if I tried to do new y of 4 at the same time, well, now I have y1 plus y of 2 plus y of 3 plus y of 4. I really just want to reference this latest result, but that was done serially, right? I want to do these two operations simultaneously, but without repeating myself too much. But this entire computation is shared between these two values. So hopefully you can see this conundrum, right? It's not obvious how you would split this algorithm up for multi-threading. So there's some examples here of how this all works. We actually have prefix built into the Julia library now. It's called accumulate and does the same thing as what we just implemented. But because plus and star and all these operations are associative, we can do some clever grouping here, where maybe we do some grouping and do some different things and clever reuse of operations in ways that we can, cache these things cleverly so that way we can reuse them. Maybe there's some promise here. And that's exactly what this magic function does. It does something really crazy here, right? It does something that's really hard for me to understand. It does the exact same it takes in some binary operation, some vector. It only works for length 8 vectors, which is kind of interesting. And then it has 5 different for loops to compute its result. And they're structured kind of funny, right? For I in 2, 4, 6, 8, so all my even numbers, all my evens, my last number, the number 6 for some reason, and then the 3, 5, 7. Like there's some really funny computation that's going on here, right? And I'm just going to say that this function was derived by magic that, we have some magical function that does this. And we can test it and see that, sure enough, it actually works. I do a prefix 8 of our plus function of the numbers 1 through 8 and test if it's the same as the cumulative sum of our numbers 1 through 8. And it is. It's doing what I want it to do. But boy, is that confusing, right? How am I, as a programmer, supposed to understand that this is A, going to work at all, and B, doing the right thing? It's kind of hard to understand what's going on. And we can even generalize this even farther to do more magic that allows for any length vector. And you'll just have to trust me that we're doing some magic here and more magic here, 2 for loops. We're using inbounds. So hopefully whoever authored this function knew what they were talking about, and these are actually inbounds. And we're doing lots of complicated arithmetic on which indices we're using. How do I go about just wrapping my head around this algorithm? What do I do in order to do this? Well, I can just see, what happens, so I can create a random vector of the digits 0 through 9 that's 123 elements long. Do a prefix, maybe let's do a prefix star here. So my numbers are 4, 9, 7, 7. And you can see 4 times 9 is 36, times 7, I guess, is 252, times 7 again is 1768, I guess. We'll trust that. And of course, you could ask for the cum prod as well. And it is the same, right? It's working. So what is this magic and how is it working? Well, we can visualize this operation with a little bit of trickery, because Julia's arrays are, very, extensible. We can do some really cool things. I'm just going to run all of this code here without telling you how it works or what's going on. It's essentially defining a new Julia data structure that will keep track of what has happened to it as you work with it. And so let's define this guy. And we now have the ability to look into its history of operations. We're calling it an access array. And so you can do our prefix operation here, where we have some sort of pattern, and you can see that we end up with an access array that tracks its history, where we can go in and see that we read from elements 1 and 2 and wrote to element 3 and so on and so forth. And you can dig into the implementation here. I'm going to breeze past this to get to the beefy stuff later today. So I'm not going to dig into exactly how this works, but you can dig into what's going on. It's essentially just recording which elements it reads from and which elements it writes to in sequence, so that way you can trace execution of any algorithm that you use. It traces what gets read from and what gets written to. And we're using Julia itself to trace this algorithm through. And now we can do something that's even cooler, and we can use Julia to visualize that history and go through this. And oh shoot, I didn't want to do all of those all at once. Well, let's see. I might have messed myself up here. I just executed too much code. This will take some time. I'm trying to move too fast. So I've created this render function here that will take an implementation and render it to a visualization that I can look at and play with and see what the order of operations is here. It's doing a bunch of timings right now because I ran the entire script too quickly. Give it just a second. Okay, so now I can go in and render the history of my operations that happened when I did an 8-element addition. And this is really cool here. So let me annotate on what Julia is spitting out, so that way we can, look and see, exactly what's going on here. So here we have these vertical lines are our indices of our array here. 1, 2, 3, 4, 5, all the way up to 8 here, right? These are the indices of our array. The small dots represent reads. So we read what the first element of our matrix is, of our vector is. We read what our second element is, and we take those two, add them together, and we get, a of 1 plus a of 2 here, right? And then that is the last time we write to the second element. So the big circles represent writes, the little circles represent reads. And then this write here, that propagates the whole way down without any other writes to it as our new second element. Our first element here never gets written to, right? So our first element always stays the same as the input. The second element is just the second element of, just the first plus the second and added in. The third element starts as the third element, right? Comes down here, gets read along with this, whatever the result of the second element here was, which was 1 plus 2, and gets added together. And that gives me my third element. So you can see here exactly how this algorithm works very visually. The fourth element now, 3 plus 4 gets added together to this intermediate result. This is just y of 3 plus y of 4. And then it gets added together with the results of 1 plus 2 and gives me the answer for 4. That's going to be my final answer for 4. And so on and so forth. You can kind of see how all of these things work. My fifth value here comes up, and all it needs to do is take this answer, right? This value after we've added the numbers 1 through 4, or the indices at 1 through 4. We just take that value, add it together with what we started with on my fifth index, and that's my fifth index. The sixth one is a little bit more interesting, right? Because we have the fifth index plus the sixth index, add those guys together, and we go down and so on and so forth, and add together the first 4 then. And because we're very cleverly, essentially using the data structure itself to cache the values and knowing when we can access things, well, now can you see how parallelization would work here, right? You can look and see that all of the things along each line here can happen simultaneously, right? Because none of these operations depend upon each other. We've separated out all of those operations. None of them depend upon each other. The next row here, well, this row now does depend upon what happened before. We need to make sure that we've run all 4 of these additions before we run these 2 additions, right? Because these 2 additions depend upon these 4 being run beforehand. And if we were to switch the order of operations here in this direction, we would end up giving ourselves errors, right? Because if I took the value at 2, say I moved this guy to happen after this read, well, then I would only I'd be missing the first value here in my sum for 4. And in fact, I'd be missing that first value in all my sums after 4, because they all depend upon this one operation. So this is pretty cool, right? We've divided up my algorithm in a way that I have parallel friendly sections, right? So moving horizontally here is totally fine and friendly, right? We can move back and forth horizontally to our heart's content, but we can't switch things vertically. So horizontal movement in my algorithm here is just fine in the way that I've rendered this. Vertical movement is verboten. That would end up giving me the wrong answer. And so that means that horizontally, I can do these things in parallel. Vertically, I can't. It's just a really cool way of doing this. And then, of course, we can go in and watch what happens as we add more and more more and more values to our arrays, right? So we can change this to say, well, let's look at 16 and go back to our plots window. And here's doing 16 values. And you can see how it extends to many rows and columns and such. And you can trace all of these things down just like I did initially. And it's really cool to watch these things happen. And it's really cool to change out, try playing around with this. Like what happens with the 17th element, right? Doing an even power of 2 is kind of obvious and symmetrical, but what happens with that 17th value? Where does that come in? And here's that 17th addition. So you end up doing more additions than you would have done in your single threaded example, but you've done it in a way that it's parallel friendly. And if you have lots of nodes and lots and lots and lots of data, this is a huge win. And of course, compared to the serial code, you can do the exact same thing here and render that. And well, it's just going to do, what we were used to. And of course, you can't rearrange any of these operations like we had talked about. So now we know which for loops are safe, which for loops aren't, and they're just structured in a way. So your outer loop here, or I'm sorry, each inner loop represents the horizontal lines. These outer for loops represent the vertical lines. And this is our algorithm now. And now, because this is safe, we don't need to do any of the things that we talked about in the previous lecture about making the @threads macro thread safe, because this algorithm is thread safe. And so you can define this, implement it, and then run our, time these things and see, as compared to the serial algorithm, the prefix algorithm, and the prefix threads algorithm, compare these 3 timings. And you'll see that the serial version is faster when you're only talking about 6 processes or 6 threads. But if you have a very, very large vector, you actually end up winning with the prefix threads. So that's the way that we can talk about these things and begin making this. So here you can see, if we do the serial thing, the naive serial code where you just sequentially go down that diagonal, it takes 1 millisecond. If you do the prefix bang, the very fancy version that does the split of our for loop and things like that, it takes longer because we're doing more operations, right? This is that fancy version. But then if we add threads to it, we can end up beating the serial version by 2-fold, because we've enabled the use of all of our cores. And so this is a cool little example of an algorithm that's hard to think about, hard to do, but you can visualize it using Julia, and you can dig into this notebook later on to see exactly how that works. I don't want to spend too much time there. And we can then multi-thread it just by tacking on. It then is as easy as adding that @threads. And so this is a nice little wrap up to our multi-threading section, because here's a really awesome example where it's just as easy as adding @threads, and you get almost perfect 6x speed up from our original algorithm, because things are nicely divided up. All right. So with that, any questions here on parallel algorithm design? I know I moved quickly, but the whole point here isn't really on the architecture to do the rendering or do the function tracing. The whole idea is to get you thinking about creative ways in which you can reduce shared state and think about ways in which you can build your algorithms so that way you have explicit multi-threaded sections and explicit sections that aren't multi-threaded. And then now you're thinking in parallel, when you can think about, hey, these portions we can can do in any order. Other portions of our algorithm we need to be sequential. That's the magic here. Awesome. We're picking up time here. Let's move on to our next notebook and talk a little bit about tasks. I think I'm going to do this one. This will probably take me about 20 to 25 minutes. So again, we'll go over on our break timing just a little bit beyond the top of the hour. But I think it's nice to tackle this right away so that way we can have the second half of our day focused on distributed and GPU processing. So, notebook 60 on tasks. Tasks are this very interesting thing. And I'm going to start off talking about how computers do multiprocessing, right? On my current computer, I have an absurd number of things running right now. Like, I really should close some things down. I really should read some emails. I should respond to some calendar notifications. I guess I have some text messages I need to respond to. All of these things are coming in while my computer is doing this, right? While I'm talking to you all, while I'm running Julia code. And I have far more than 6 things running at a single time here, right? But I only have 6 cores in my computer, as we've talked about. But it has the impression of having hundreds of things going on simultaneously, right? I have Zoom, I have Julia. These things are dynamically working together. I'm using all of my cores with Julia, and yet I'm still able to talk to you with Zoom, still able to share my screen. How is this happening, right? So the answer is that our computer is doing what's called multitasking. And for those of you who lived through the 90s and early 80s, you'll remember when computers were single task machines, where you had a single floppy disk that you put into your computer, and that would be the only thing your computer could do, right? There weren't multiple applications that you could run at a single time. There weren't, you couldn't command tab out to other applications. You had boot up and run a single app at a time. But at some point in the 90s, computers began introducing multitasking. And this was before there was multiple processors, right? Before we ever had more than one processor in a machine, you could actually run more than one application at a time. And the way that the computer did this was by what's called preemptive multitasking, where the operating system would sit at the top, kind of like a wizard, and just say, hey, VS Code, you get access to the processor now. Zoom, you'll get access to the processor in a few milliseconds here. Hang on to what you're doing, and we'll just dynamically switch back and forth what things are doing so quickly that it gives you the appearance that things are running simultaneously. So that's how our computers work, right? We have computers that do lots of things, that manage all of our inputs, all of our outputs, delegates control of our processor between Julia as well as everything else that's being run. And this is called preemptive multitasking. It's not really doing all of these things at once, but it's giving us the appearance of parallelism. We think about all of these things happening simultaneously, but it's not really simultaneous. It's just that switching, and our processors are so fast that it feels like they're switching back and forth so quickly that this feels simultaneous. And this kind of task switching is perfect for operating systems, where really it's 90% of the time, it's just waiting for me to click my mouse, right? It's just waiting for me to do something, to change applications or things like that. And then it can dynamically swap what's happening. And this is a perfect situation where you're waiting for user input. You can swap tasks back and forth, give the appearance of multiple things happening at once without actually using true parallelism. So this is what's called preemptive multitasking. And the preemptive part of it is that wizard, that operating system wizard that's choosing who gets to run at a given time. Julia similarly has a task system that does the same sort of thing within Julia itself, where you can have multiple tasks that, instead of having a wizard that chooses which gets run at a given time, they just cooperate. And so you'll have a task that says, hey, I'm done now, and another task will jump on and do its work at that point. And this is what's called a cooperative multitasking. Other languages sometimes call this coroutines or green threads, which I find both of those terminologies very confusing as compared to what to extend your existing knowledge. If you're new to these sorts of things, I introduce those names here because of if you're coming from other languages, you might find those helpful comparisons. But I like the cooperative multitasking verbiage. It makes sense to me, where we have multiple tasks on a single process that simply will flag to Julia, hey, we can potentially run your swap back and forth who gets access to our single core of computation. And we'll just choose who gets to run based upon, talking to Julia and saying that, we're ready to run now or we're not ready to run. So tasks work best, as I talked about, like kind of that operating system sort of paradigm where you're waiting for some external condition, something in the outside world where you don't need to be doing some computation. You don't actually need access to the processor. You're just looking to see, hey, has something changed? And if something's changed, then let's do a little bit of work and then say we're done and allow another task to do this. So a great example here, a great way of examining this or waiting for an external condition is our file system, right? On our computer, we have a file system that we can look for changes. And there's a nice built-in standard library called the file watching, where we can create a results folder and watch that folder for changes. So you can say watch folder and results. And then the second argument that we pass in is a timeout. So it'll just sit here and Julia will just wait for 5 seconds. And if something changes inside this results folder within that 5 seconds, it'll tell me what changed. If nothing changed, it'll just give me an empty event back that says, hey, nothing changed. Let me change this to about 10 seconds and go into my VS Code section here. So here I just created this results folder here by this make dir results section here. So now in my file browser, I have this results folder. It's empty, right? And if I start this up and say, let's watch this folder for 10 seconds, and while I do it, let's create a new file that just says test.txt and go back to Julia here. So I created a new file, it opened, which is kind of annoying. But what my watch folder returned here was because I did that quickly enough within those 10 seconds that I got an event back, right? And Julia returned faster than 10 seconds and said, oh, aha, something changed in this folder. The thing that changed was this test.txt file got created and gives me a file event that describes that occurrence. So Julia will happily sit here forever. If I happen to give this without a timeout, it'll happily sit here forever, endlessly waiting for something to change or for me to interrupt it with a Control-C, for example. I could do that and maybe hopefully, yeah, there we go. And get out of, with Control-C, interrupt the execution of its waiting. But I could also, instead of waiting forever, I could set this up as an asynchronous task. And just like our primitives from before, this is another macro primitive called async that simply says, hey, let's spin up a task that can run at any given point, that Julia can cooperate amongst all the tasks that are running, and we'll just watch this folder for a change. And you can see that the task will just sit here. It's a runnable task. It can be swapped to, it's just waiting for some change. I can grab now I can run other code in Julia, right? I'm not blocking anymore. I'm not sitting here waiting. I can actually run other code, including creating files, right? So I could create another text file here called 0.txt. And now if I go back to my task, you can see that the task is actually done. It's done its work. It's finished. It's completed, right? Because we've swapped back to the task and it's found that, hey, there is something that changed and we can fetch the answer back. We can fetch which file got changed. And sure enough, that 0.txt is what we created in our results folder. And now you can imagine taking that file and processing it with some external processing thing. So the mental model here is you could imagine you're interfacing with some external experimental system that dumps result files or log files into some folder. And you want to process those as soon as they come up. You don't want to sit there and spin forever. What you can do is you can create a task that will just wait and explicitly say, hey, something else can run while I'm waiting. There's no need for us to just sit here and spin while I'm waiting. We can do this asynchronously. It's not going to use true multi-parallelism, but we don't need to because we're waiting on some external event. And so Julia, switching back and forth between tasks, can happily check in on this, see if something has changed, and do it. So we can bundle this process up into a repeatable task where you can have this function called process folder, where we take in some directory like that results folder, where we're waiting for results to get dumped in, and just watch that folder for changes. When we get a file that changed, let's process it, right? Let's do our log processing. Let's do our results processing of some sort. This here, just to kind of emulate this, let's just copy it into a processed results file, a folder. And so you can, pretend that this is doing real work here, but it'll just wait until things happen. And then once that happens, it'll go. And this is an infinite loop, right? While we're looking for this is done condition, which is false to begin with. So we're not done yet. So while we're not done, let's just infinitely loop, just watching our folder, seeing if the folder changed, and then process that path. So we can define this, run this, and then remember, we want to asynchronously run this function, so that way we can do other things at our Julia system while this is a task that's on our task queue waiting to be running. You can see that it is a runnable task, right? Again, just the same as before. And just as before, we can create, so let's just kind of look in. You can use readdir to see, what values are in our processed results function. So if I readdir right now, there's nothing there, right? I've not created any results files yet, so there's no results that have been processed yet. But if I create another file there, well, sure enough, it'll output, here we got the text output saying we're processing the results. And if we read that directory, sure enough, here is our one element array that has that single processed results back. And this is just happily running asynchronously. It's not running in parallel, it's running asynchronously. It's still we're only using one core of compute here, but we're giving the impression that there's two things happening at once, because one task is just waiting for something to happen. Our other task, our Julia REPL here, is also just waiting for us to type in and run some code. And so when I do that, sure enough, I process it and I get my other thing there. And of course, then I can turn on my done flag, and now I'll no longer process any more results. So I create my fourth value here and we're done. And in fact, you can see that the task that I had created is also complete. We've finished our task. It's done. It's no longer on our task queue to run. We're no longer going to be swapping to it as need be cooperatively. So we can clean up our kind of demo here, remove these folders from your system if you want to clean them up. So that's a nice little concrete example of using asynchronous processing and a really good place for it, right? Where we're doing asynchronous processing because we're waiting on an external event. So let's take a little quiz here and just kind of look at these 3 for loops here, right? So if I have a for loop and I loop 10 times for I in 1 through 10, I loop 10 times and just, sleep for 1 second in the middle of the for loop. How long is this for loop going to take? Well, you sleep for 1 second, 10 times. Julia, as we've been talking about, for loops by default run serially. So we're just going to sleep for a second, 10 times back to back to back to back, and it's going to take 10 seconds to do. That's simple enough. What about this one? Now, this is an interesting one where we asynchronously sleep for 1 second. How long is this for loop going to take? And I encourage you to think about it before running it. I just ran it myself here, and you can see that it took no time at all. Why is that? Well, remember what the async macro does, right? It just creates a task, right? Let's look at what this does here. When I say t equals async sleep for 1 second, it just creates a task that can run, and we can switch to and see if it's running. And of course, it's just going to wait for 1 second, and then it's going to be done. And so when I switch to it, it's going to see that, oh yes, my sleeper timer has fired, and now we're done, and we've completed. And so all this is doing is it's timing the time it takes to kick off 10 tasks, which of course happens in no time at all here, right? 100 microseconds or something like it. Now, what about this one? This one's interesting because it introduces a new macro that I've not introduced yet, this @sync macro. What do you think that will do now? So I've added this @sync outside of my for loop. And well, if you hover over it in VS Code, it'll tell you its help. And it says, hey, let's wait until all the asyncs that we've created are complete. Oh, that's cool. So if we wait for all of these asynchronous tasks to complete, how long will this function take? Well, let's copy it and paste it down in my REPL. And you can see that it takes just a little over a second. So what's happening? Well, it's creating 10 tasks, right? It's kicking off 10 tasks all in less than a second, right? Very, very, very rapidly creating 10 tasks from this for loop. And then this @sync is just looping through those 10 tasks, checking in on them cooperatively. They're all just kind of cooperatively bouncing back and forth saying, hey, I'm not done yet, I'm not done yet. And then after a second or so, it'll bounce through all 10 of those tasks and see, yes, they're all 10 done. Now we can complete, and now we can progress to our standard, now we can resume standard serial execution after this sync block has completed, right? So we can use async and sync to kind of, set the stage for, things that are wrapped in async are places where we can explicitly tell Julia, hey, these things can happen at any point. And sync can say, all right, now I'm done with my parallel mayhem. After the sync block completes, let's wait until everything comes back together. And now we can go back to our standard mental models of serial execution. So that's pretty straightforward, right? So what if I had a function that actually did real computational work, right? Sleep, when you ask Julia to sleep, it's just going to set a timer and wait for that timer to fire, and will just wait for that to happen. If I'm actually doing core arithmetic or asking my doing some sort of algorithm that is doing some computation requiring CPU access, right? Then this is going to behave differently. So we can create this work function here where, for the time that it takes, let's make this, be about a second again. So let's see here if that takes, so maybe like say, work for 800,000 iterations. And I don't need to know what this work function does. It's just doing some sort of computation that if I do 800 million iterations, it's going to take about a second, right? And so now if I do this for 800 million iterations, and I do the exact same thing, right, where I use this time, sync, async for in 1 through 10 work for 800 million iterations, how long is this block going to take, right? Think about it. Each iteration takes about a second. We're telling Julia, hey, you can do them asynchronously, but we're still only using one core. And so unlike the sleep example, where sleep is just waiting for some timer to trigger, here we're actually doing real compute. And so even though our tasks are cooperating amongst each other, even though they're sharing our processor, they all really need processor time to get complete, right? And to actually do their work, they all need to be scheduled. And so they might run out of order here, but they all need to be scheduled onto our processor core to get things running. And so this will actually take 10 seconds, even though we flagged it with async. We're saying that, hey, this work can happen asynchronously. We can do this at any point. It doesn't matter because we still are competing for a single core of execution. So sleep, the answer of what's happening is that sleep happily cooperates with the tasks that we have. You can actually see how this works by jumping into the Julia definition, the function definition for sleep. And let's see, can I do that? Oh. So there's an edit function that can bring up the editor. I need to get my VS Code here set up so that way it actually shows in my editor properly. But here, this is the Julia, the built-in Julia implementation of sleep. And it's using our multitasking primitives to simply wait for a timer to fire. And this wait function here, well, we can see how that works. It's just explicitly cooperatively talking between tasks, talking to the task system saying, hey, I don't have real work to do here. I can just wait for this timer to fire and another task can run at this point. So you can fetch values from tasks. So here you can see I can wrap up multiple things in an asynchronous task. So I can sleep for 5 seconds and then generate a random number, bundle that into a task. You can see that it's a runnable task. I can wait for it to complete, and then I can fetch its value. And that gives me the random number that was generated by this asynchronous task. And if I do this in quick succession, you can see that it'll wait 5 seconds and then now it blocks and it'll fetch. And if I did this inside another asynchronous task, this wait is explicitly saying, I'm okay to, to jump to another green thread or another task to do this. And so you can see that often you're inside a while loop where you're waiting for some condition before proceeding, and this will work really nicely with our entire task system. So you can see how that happens. So fetching, if you fetch before a task is complete, it'll automatically block. So this will wait for 5 seconds until my random number is generated. But now we have this really nice infrastructure to think about asynchronicity, to think about tasks that can run in the future, that will have some value in the future, that can cooperate with each other and can get things done. And in fact, the really, really cool thing is that the new threading infrastructure in Julia 1.3 plus builds on this and uses the exact same terminology. In fact, it uses the exact same core data structures as tasks. The only difference is that we then say, instead of needing to be constrained within a single processor, they can actually float amongst all of our threads. So I can go back to this example here, this work example, right, where we're doing our work 800,000 times. I do this with the async primitive to create a task, and it'll take 10 seconds, right? This is what we had seen. This is how we had gotten this up and running in the notebook. But now if I do this and I change this async macro to a threading macro where we say, threads dot at spawn. This is how you spawn a task that can jump between multiple threads. And now this will actually use all of our compute cores that are available to us. And it's exactly the same primitive, right? We're just saying that this can run at any point. And the only difference between async and threads.atSpawn is that threads.atSpawn says, hey, I can use any of my 6 cores. And since I have 6 cores, I can do this 6 times faster than it would have taken otherwise. And this threads.atSpawn is exactly how the @threads loop works. When we saw that in our earlier examples today, this allows you to just spawn off individual tasks that can do real compute work on any process. And you can see what happens here, right? I can do t equals threads.spawn. It gives me a task that's going to have a value that I can fetch in the future. And I just don't care which thread it runs on. So this is tasks, and it's the core infrastructure for multi-threading. It's also the core language that we're going to talk about when we come to distributed computing, which is where we're going next after this break. So I think that wraps up this section quite nicely, where we've now introduced really concrete verbiage around chunks of compute that can happen at any point. We've used the async macro, right? The async macro just kind of schedules a task that can cooperatively multitask on a single core and is nice for UI kinds of things, waiting for user input. Or we can use threads.atSpawn, which also creates a task, but now this task will just schedule dynamically across any of our compute cores. If we only have one thread, if threads.endthreads is 1, then it'll act exactly like a task. It is, in fact, exactly a task. But if we have more than one thread, well, then we can actually do compute on multiple cores simultaneously. So this gives us a language here to talk about these things, about how we're actually doing compute and doing them in parallel nicely. Async to create and start running a task, just kind of kick it off and say, I don't care when this completes, until we sync back up again. And sync will wait for all the tasks that you've created to complete. And now we can reason about asynchronous runs that might return a value in the future, and we can fetch that value back with a fetch, or we can wait for it explicitly, or you can synchronize them all together. And then, of course, the new hotness is, threads.atSpawn is exactly the same, but doing real parallelism. So that is the magic here. Any questions on tasks or how this interfaces with multi-threading? If not, then we're in good shape to tackle Notebook 70 on distributed compute when we get back from our break. This is where we're going to really start, leveraging distributed compute on multiple nodes, and we'll start looking into how Julia Hub enables this kind of workflow. Yeah, we'll keep updating these notebooks on that GitHub site, and I'm going to be bringing together all of our notebooks together on that one site, so you can keep pointing to that as we go. We'll make sure that this is the latest and greatest things there. A good question before we take our break on, will I get into trouble or choke the system if I spawn thousands of tasks? And the answer there is actually no. You can spawn many thousands of tasks and you'll do just fine. It goes into a depth first queue that can indeed handle many thousands of tasks. And it works really nicely amongst libraries that can even spawn tasks, and you don't need to worry about them. This is how we'll eventually get matrix multiplies to not oversubscribe, is they'll key into this system where they can spawn up tasks as well. And then they'll just happily coexist with all the threads that you spawn. You might start seeing limits if you're doing on the order of millions of tasks. Then if the individual work unit is smaller than the coordination of that task queue, you might see a little bit of overhead there. But in general, we've strove to reduce the overhead of this work queue as much as possible. And so you can do this. A good question about, how would I kill a task, right? So say I have t equals async or potentially sleep, say a super long sleep value here. How would I kill this or stop it from running? The answer here is a little bit tricky. And I think the easiest way to do it is to use throw to. So I can throw an error to this task. So I can say, let's just throw an interrupt exception to this task. See, I think that's going to be it. So you can see that my task is currently running. I can throw an error to that task, and that will error that task, throw an error, and if you're waiting on it or something, then that error will propagate. But this throw to allows you to throw an interrupt to a task, and I think this would generally be the best way to interrupt a task or kill it. We don't have this isn't a true process, so you don't kill the process. Instead, you interrupt the execution or throw an error to it. This would be how you would do that. That's a good question. All right, with that, let's take our 10-minute break. And when we come back, we'll talk about distributed compute. It'll be about 27 past the hour that we come back. I need to unmute myself. All right, welcome back, everyone. While we were gone, we had a few good questions that I figured I would wait to answer until we all came back because they're good questions. One is, how can you make sure all tasks are either completed or killed, or if you don't know their task and you don't want to throw an error. The key thing is to, just like when you're doing array programming, you want to make sure that you keep a hold on to all of the values that you want to use. The same thing is true of tasks. And so if you wanted to, for example, you can put them in an array, right? You can create a lot of async tasks, sleep 100 for underscore and 1 through 100. This will create 100 tasks that I don't have explicit names for, but all are, going to be running here, right? And they are all going to sleep for 100 seconds. And of course, they're all, interactively running and held on to each other. And this would kind of be how I would recommend you, program if you have lots of tasks. Make sure you put them in arrays so that way you can, reference them and get their values. You could potentially then, use pointwise broadcasting to say, fetch all the values from this array of tasks, right? Fetch all the values from this answer, or potentially, you could wait on all of them to complete, right? And this will wait until every last one of those 100 tasks has completed. And, or you could throw to all of them. The same concepts is true for all of these things. So that's kind of how I encourage you to do this. Make sure you just keep tabs on these things. You don't want to necessarily, if you want to ever refer to a task back again, well, you need to have some reference to it to talk about and think about reasonably. A good question from Vish about channels. And I didn't talk at all about channels here. Channels are kind of the way that tasks can communicate amongst each other. And it's, you can kind of think of it as a pipeline. And I don't have this in our document, in our notebooks here, just in the interest of time. This is well included in the Julia manual itself. There's some really nice examples on asynchronous programming that you can check out. And the idea behind a channel is that they are the way in which you can negotiate data back and forth between asynchronous tasks. And so this is how you can move data back and forth, grab data off of a channel, put data on another channel. And the nice thing about channels is that they automatically wait for new things to come to you. And so that concept of waiting for a value is explicitly encoded into a channel. That's kind of like, you can think of it as a pipe with a read end and a write end, and you're putting data through. And it works really nicely with our tasking system because it'll automatically wait for values as they come, and it's explicitly thread safe and task safe to work with these things concurrently. So you can have multiple writers, multiple readers, and it handles all of the synchronization for you. And so you can create a channel with 32 elements like this, or explicitly say what type things are going to be for type stability and performance, but lots of details here. All right, with that, I think let's charge ahead and talk a little bit about distributed compute. And then, so we have 2 sections left in the last hour and a half. I'm thinking we might just skip the last break in the interest of time, if that's all right with folks. I'll give you a warning now that we have a lot to cover, and we've made up some time, but still have a little bit more time to make up in order to cover everything well. So let's charge ahead and so we just have 2 notebooks left: distributed compute and GPU compute. The GPU compute we're actually going to run on the cloud. And then once we're on the cloud with the GPU machine, we'll also loop back to a little bit of distributed compute again. So remember how I talked about at the beginning of today, how distributed compute works, where you can kind of imagine things as having, multiple machines running around like a mad person typing into all of the machines. That's exactly what distributed compute is. You can think of it as multi-process parallelism, where you have lots of independent Julia processes that you want to communicate with and split up work between. And just like independent processes work within your operating system, you no longer have access to shared memory. These are independent processes, and it's like launching a whole slew of Julia processes. They can't reach into each other and look at memory. They can't have shared state in the same way that multi-threading does. Which is both a blessing and a curse, right? A blessing in that we don't have the same kinds of shared mutation problems that multi-threading sometimes runs into. Those same kinds of race conditions are a little bit harder to encounter. You can, of course, still program in race conditions if you're not careful, but it's a little bit harder to run across because you're in explicitly siloed Julia processes that you're explicitly talking to and using and running. And so this is all built in to the distributed standard library. So you bring this in just saying using distributed, and this is your way of talking to essentially other Julia processes and even spinning up other Julia processes. By default, we of course only have one Julia process connected to our machine, right? And we might have multiple threads on that Julia process, but it's just a single process that's doing all of its work. So you can look and again see, remember we have 6 physical cores here. So if I didn't want to use multi-threading, I could instead add multiple processors or multiple processes, add additional processes to my Julia folder or to my Julia instance that can then talk to each other. And I'm going to start all of these up using the same, project file as what I had before here. And let's see, I think this might work. Is that gonna work? We'll see. This @dir here will just make sure that I'm in the same directory as all of my it makes sure that all of my workers have the same project and they're all using this same the same environment, which is important, right? I want all my workers to be using the exact same environment as my master worker. So this is adding Julia processes. It's actually spinning up a bunch of Julia processes in the background that I can then communicate to. So I've added 6 workers that I can communicate to. So now I have a total of 7 processes that are hanging around. And in fact, if I go to Activity Monitor here and search for Julia, you can see that I have a bunch of Julia processes, including the ones that I started up. Oh man, it's so tiny. I'm sorry. But you can see, here are those 6 processes that I just started. The others are, have been running for longer. You can sort by the CPU time here. These 6 are the ones that I just started. And you can see that they've not been running for very long. These others have been running much longer, including my main session, which I started yesterday, right? It's been running for 14 hours. All right, so this is how we have our setup now is that on our one machine, we have our master Julia process and 6 workers that are connected to it. And I can ask, just like I could ask what thread I'm on, I can ask what worker I'm on or what process ID I'm on. And we can communicate to our other nodes. And in the same way that we have worked with tasks, right? We have this idea of a chunk of computation that may return in the future with some value. The same thing applies to distributed compute, where I can say, hey, let's spawn some computation, kind of like threads.@spawn, but this is using distributed.spawn. We can spawn on, say, process number 2, ask for its ID and some random number. and do that. What we get back is kind of like a task. It's called something different. It's called a future, but the concept is the same, right? It's a promise of some answer in the future where we can fetch it, we can wait on it. The verbiage is all exactly the same as tasks are, where we have some computation that can run asynchronously. And like before, now we have 3 different ways in which we can run processes asynchronously. We can run them as tasks. We can run them as tasks. We can, have them run on all the same core, just schedule amongst each other, cooperate nicely. We can run them on different threads, have them all work nicely, on a single node, or we can schedule them amongst different processes using distributed. So now we have 3 ways of using all exact same language, all the same fetch, waits, synchronize kinds of language. The only difference is how we kick them off, right? We used async for tasks. We used threads spawn for threads, and now we can use spawn at for distributed. Very similar verbiage, just different ways of computing. So just like before, right, the amount of time that it takes to spawn a task is no time at all. It's just communicating with our other worker. And then the actual time happens when you fetch the answer, right? The remainder of our sleep and however long it takes to fetch the answer happens then. And of course, then we can repeat the exact same examples we did before, right? Where if we just time how long it takes to iterate over all of our workers, spawn at each worker, which worker we're working with, and sleep for a particular given time. Remember our workers here. We've not run this function yet, but it's just the array of process IDs that we can communicate with from our master node, our current MyID, right? Our kind of coordinating node is the way to think about this master node. It's when you're using distributed compute, you don't use this node to do actual compute, but rather it's the coordination node that you have in your master node. So if we run this time loop here, well, it's going to take no time at all just to kick off these workers, right? We're just kicking off all of the tasks and not waiting for them to complete. Just like before, though, we could add this at sync in there, which will wait for all of our workers to complete, and it'll take a little over a second plus some overhead. I think that there's some compile time there the first time I ran it, so it just takes 1 second to run this and wait for all of our workers to complete. So this is exactly like tasks, except now we're executing code on a separate process which has its own state, right? It has its own compute resources. The operating system now will take care of scheduling it onto our processor, sharing it amongst Zoom and Mail and all the other things running on my computer. And we can now do this work function that we introduced in the last notebook, define this work function, and then time, say 1 billion iterations takes about a second, and do the same sort of game that I had before, where I iterate over all of my workers, and it'll actually do this work in parallel across my workers nicely and easily. Now, this isn't very helpful to just repeat the same work on all of my workers. You might have noticed what this work function does, right? It's again playing around with different ways of defining pi, and it gives me a value of pi that's actually pretty accurate, right? 3.14159 some. I can see what the value of pi is just by asking Julia and see how far away we are after 1 billion iterations of this work function. This is just the Taylor series expansion of the pi evaluation, and it's doing some reduction here. We're adding into a bucket of the Taylor series elements, right? And it's a pretty straightforward computation. So let's use some of our knowledge from our previous lecture on re-implementing this in a way that's parallel friendly. Well, instead of just adding it all into a single bucket and adding the terms from 1 through n, we could explicitly ask for just pass in a set of terms that we want to use with this range, say, and just compute a partial sum of the partial Taylor series elements, right? So I could ask for the partial pi, oops, I need to evaluate this function. So I could ask for the elements of the 0th index through 999. In this case, it's easier to be 0 indexed. So we start with the 0. So the first 1,000 elements of pi, gives us 3.14, three digits of accuracy. You can see, how close we are to pi here. And then we could get, say, the next 9,000 elements. And these elements, if we take A plus B, then this gives me my total Taylor series, right? And then you can see what this value is, and we've gained accuracy here, right? Now we're 4 digits of accuracy instead of just 3 digits of accuracy. And so on and so forth, right? You can grab any mix of the Taylor series coefficients, and it'll just add those coefficients together, right? You could grab some random values in the middle, some large number here, right? We could grab, say, just a whole huge chunk, 0 through 10 million or so, to get a slightly more accurate answer. Or you could divide up this chunk across different workers. So let's do this. Let's grab our batches and set this up. We can do exactly the same sorts of things as we did before. And say, let's do 1 billion iterations of pi here. So our total range that we want to get is from 0 to 1 billion. And we can create an array of futures that will hold our answers. And then just go through, loop over all of our values, get these things, oops, I'm going to hit enter down here. Do this iteration over our workers, enumerate our workers, split up our batch, do some careful consideration of how we split this up and get the sum of them all. That's pretty straightforward, right? We have this array of futures now. Instead of having each element working with a single, in-memory location like we did with threads, now we just have this array of task-like things that are a promise of a value that we could fetch, and we could just fetch all of the values, right, and get all of these partial results from our 6 workers. So here you can see, what the first chunk is, and then we add all of these partial results together to give us our final answer, which is the sum of all of these futures fetched together, which then should give us a really nice close approximation for pi. And we're within 9 decimal digits now, which is pretty cool. And we did this in parallel across all of our workers, and it's pretty straightforward to do. It's a little annoying to carefully divide up our workflow this way and manually add in all of these arrays of futures. There's got to be an easier way. And just like that threads macro, we have a distributed macro that we can tack in front of a for loop. And so we can play a game here with our total range. Let me grab, where did that go? We can play a game here and split up our elements and just grab the partial results, and we can just kind of play around with how many answers we want or how many iterations we want, and we just compute the partial pi of each one of these, say, 100,000 chunks, and the distributed macro will automatically divide it up amongst all the workers that we have here. And just like threads, we're not explicitly encoding how many workers are connected to my machine. It just automatically will scale out to however many workers we've connected here. And so all of these workers are local on my machine, but the same concept works nicely. Now, Jean-Philippe asks the very beautiful next question. This isn't just distributed for here, right? We're not just distributed for loop over this. We're actually we're encapsulating a plus as part of our thing, and this is doing a reduction. So I'm sure many of you have heard of the, kind of magic of MapReduce. And, there's this huge, Google scale kind of terminology around MapReduce and how magical it is. And it's kind of, when I first started hearing all the marketing around MapReduce, it sounded very magical, but the core thing that it's doing is a very basic operation. It's mapping some operation. So you do some map here of some operation. In this case, we're mapping partial pi over all of the elements in the way we've divided up our iteration state. We do this map, and then we reduce with a plus and to get the sum of all of these things. And so why is this different from threads for? Why do we do this distributed plus for? Well, the answer is that we have 100,000 elements here. We've split apart our problem, our 1 billion iterations, into small chunks. And we have this split into small chunks. So that way, we can distribute this as needed across our entire for loop. But we don't want to communicate all of these results back. Remember, they're going to all be happening on different processes, which might even be on different computers on a network connection far, far away. We don't want to communicate all 100,000 of these results back. We really just want to get 6 results back from my 6 workers. And so each worker can do an intermediate reduction of a plus on its own accord, and then just give me a single answer back. So you can time this evaluation. You can see that we can actually do these billion iterations faster than it takes to do locally, and we get the right answer that we want back here. And we're assigning P to be the result of this entire MapReduce loop. Where we get the result. We're leaning on the distributed standard library, and it's really just doing exactly the same thing we did up here. It's just leaning on the standard library to do the work of spinning up all the tasks, getting them to their appropriate locations, and doing this. And it's a nice and easy way of doing it. So that's why we do the threads for. And this really comes back to data movement, right? Because moving data around is expensive, especially once we start talking to moving between multiple boxes, which is where these multiple workers might live. The way I spun this up right now is that they're all on my same box, but they could potentially be elsewhere in the ecosystem. And I'll show you how that works in the next hour. And so if we have to hit the network, or even a high bandwidth interconnect between machines, we're talking about a very long wait to get our answer back. And so we want to minimize the amount of communication that happens between our workers in moving data around. And so that's why it's nice to encapsulate this reduction as part of the way we spell our distributed for loop. So that way workers, no matter how many workers you have, can do the intermediate reductions and just send me back the number of answers that my master node will then reduce. So if I have multiple values that come back, right, this is just going to take whatever the last value is of my for loop, right? So I could have other things, going on here. I could even have print lines. I could do funny things here, all sorts of other operations. What it adds together will be whatever the last value of my for loop gives back. That's kind of the Lispy way of thinking about things. The return value of my for loop is the last expression that I've run here. And so it doesn't matter how many operations I do in this, what it's going to sum together is going to be whatever happens in the final line of code in my for loop. So that's what the plus operates on. And this could be a fancier operation than plus, right? I could potentially say, let's do a distributed vcat of all of my values here. And this will just vertically concatenate all of my answers together. And this will work just the same, but now instead of adding them all together, I get a 100,000 element array back of all of my values, right? I get an array because I'm concatenating them all. I'm going to send a lot of data, but I'm only going to send it once. And so VCAT is another very common reduction operator here if you want all of the answers back. But of course, in this case, we know we just want a sum, and we can do that intermediate sum and then only send one answer back to our master node to get our final answer. So that's how that works. And the name of the game is just reducing overhead, just like we've seen all throughout. We want to reduce communication overhead, and we want to do that smartly, leveraging the syntaxes that we have available to us. Sometimes you do want to see those intermediate values. One way is to do that VCAT reduction, right, which is kind of a cute abuse of Julia's array infrastructure. Much more straightforward is to do a PMAP, which works just like map, but does it in parallel across all your distributed workers. And this is potentially one of the easiest ways to do parallel computation, is just p-mapping everything across. You just take a function and map it across your values. And this will give me all of my values. And then of course I could sum these myself or look at them afterwards if I don't need a sum or something like that. But if you have a large computation relative to the number of return values, PMAP is nice, right? Because then you're getting a single result back from all of your answers. The amount of overhead that you'll see, you can play a game here, and actually we have our total range here, right? Our total billion values. And again, remember, if I time my partial pi of my range, it takes about a second to do. If I PMAP this, my partial pi, and remember, I can manually split up my range with kind of a clever array computation, or now since I'm on Julia 1.5, I can do iterators.partition my array into multiple points, right? And I can partition my range into, say, 1,000 element chunks. And we can do this and we'll get a single result back for all 1,000 chunks. And this will take a long time because of all the communication overhead that needs to happen, right? Maybe I did too many here. This might be annoying. I didn't quite think about how long this was going to take. It's going to take a while because I'm partitioning my data set into 1,000 element chunks. That means that if I have 1 billion elements that I'm trying to compute the values of, I have a million values that I need to send back. And the communication overhead here is going to be significant of all of these values. I'll let this run a little bit longer before trying to interrupt it. Interrupting parallel tasks can sometimes be dicey. There we go. So you can see that it didn't complete. It returned me all million elements here of my answer, but it took a long time because it needed to communicate all of these things. And the communication overhead is swamping my computation that I want to do. So again, I can play this game. Let's make this 2 orders of magnitude bigger. And now it takes significantly less time because I've significantly lowered the overhead. Now I'm only sending 10,000 values back from all my workers. I can, reduce my overhead tenfold again. And now my overhead is on the order of, or even less than, the actual compute that I'm doing. So this is kind of a game that you can play, and it's a really nice, easy game to see very tangibly the overhead that we have in sending values back and forth between my worker nodes and my master node here. All these values that I'm getting back here are values from spawned computation that I'm explicitly communicating with workers and sending values back and forth, potentially over the network. In this case, they're all living on my machine right now, but they could potentially be living on a network to get this going. So when do you use the @distributed macro versus when do you use the PMAP macro? Well, the answer is, use PMAP if you need all these values. Use @distributed if you can express things in a MapReduce. If you have a reduction, then there's no need to have many thousands of elements coming back. You can reduce this, and you can see here. Let me go back to my distributed for loop here, and we can play around with this a little bit more. So we can do exactly the same thing, and instead of manually doing this, let's use iterators.partition again. And if I partition my range here, remember it took a really long time to partition it in even 10,000 chunks. But because I do this, shucks, right? I need to collect this. This is something that we're still working on improving support for this partition. I need to collect this. But you can see that this is significantly faster, even with 10,000 elements here, because each worker can do the intermediate reduction and only needs to send 6 values back. And so this is faster than a PMAP now because we've reduced our communication overhead to just 6 values that we get back from our workers. So that's where the trade-off comes in. And again, it's just a game that depends on your own data movement costs, how much it costs you to move your data around between all these workers. And potentially there may not be data movement costs if, for example, you can split up your data so that way you're hitting an S3 bucket and each worker just grabs its S3 bucket value that it needs to work from, and you're using cloud compute. And then each worker handles its own thing and can send its computed value back, and you can structure your code that way. That can be very nice to do. All right, so that's the difference between PMAP and distributed. It's the concept of embedding the reduction into our distribution. So yeah, min or max are awesome functions to use with distributed. You can use any function that takes a binary operation, right? And so I could do, say m equals distributed min of all of my values here, and that'll just return the smallest answer that I got back, right? And this gives me the distributed min. I could do something different here, like some random value, and I'll get the smallest of my random value. And again, it's going to discard whatever this partial pi result was and just give me the minimum random value across all of my workers or whatever I'm doing here. Lots of really nice things that you can do. Any binary function you can pass in. So it can be, some arithmetic, it can be some fancy function, it can be minimum or max, or it can be some function that you write, right? This can be any arbitrary function. But this gets us to our next section where, each node here, each worker, each process is completely independent. It's like me going to my terminal here and spinning up a bunch of terminals where I, have each tab and I start up Julia here, have another tab start up Julia, have another tab start up Julia. I have all of these independent processes, and I need to make sure that the state amongst all of them is consistent. And so just like I need to send data to my processes back and forth, send data to process and results back, I also need to send code to my processes to make sure that they all work these things together, and each processor these things. And so one of the macros that I've glossed over that we have littered in the code, the notebook above here, are these @everywhere macros that I've not talked about, but they're actually very important in telling in synchronizing the state amongst all of my processes. So for example, I can create a function called hello world, right? And go to my terminal here, just type hello, it says hello world. But if I tried to run this function on my second process, one of these workers, and I can happily spawn this task, but when I go to fetch its answer, the answer that I fetch is actually an error. And the error is that hello was never defined on worker number 2. Right? And again, just think about this. It's just that, it's as though in a single Julia session, I wrote hello equals hello world, and then I expected to go to another Julia session, type hello, and have this work, right? This is exactly what this distributed compute is doing. And so in order to make sure that all of these things get defined at the same time, well, all we need to do is change this to say @everywhere hello. And then when we spawn this will actually work, and we can fetch our value now from our second worker, and it'll say the string hello world, because we've now defined this function everywhere. So when we're talking about this, we're talking about, communicating with our workers and getting these things, getting our code state synchronized. This also extends to multiple nodes. So we now have two good questions in the chat about how multiple nodes work if they're on different machines. And just like you want to synchronize your code state, you also want to synchronize your file system state. So that way all of your file systems are in the same they're in the same state, right? You want them all to be having the same view of the world. So you want to make sure that when you spin up multiple nodes across potentially many nodes, that your architecture, your infrastructure is putting them all in a way that they can reference the same packages, that they have access to all the same packages, and that this can also apply to pre-compiling. So for example, if I have a package that I want to use and I bring this in on my master node, I just say using statistics, and I tried to do some computation that uses a mean which comes from the statistics package, this too will error, and it says mean is not defined because I didn't define statistics on my second node. So I want to say everywhere using statistics, right? And now I can do that and do that remote computation because I've now defined this package elsewhere. This also applies to pre-computation then as well. And so if I were to use a package that wants to use pre-compiled code, well, I want to make sure that it's compiled on my master node. And then because since I'm all on the same file system here on my own local node, I want to be sure that using statistics runs first to pre-compile it if necessary. And then everywhere using statistics, then all my workers will see my file system state, right? They're all on my local machine, and they can all pick up those pre-compiled files. If I'm on separate machines, well, then I need to rely on some architecture, some underlying architecture to make sure that the code, the file system that gets spun up on my remote machines either has the precompiled files in place for me, or has the file system in a way that I can be sure to use those. In general, the precompile time generally doesn't overwhelm your total compute time. And so this is kind of an optimization to precompile all the packages that you're using. But if you need to, the infrastructure you're using to connect to remote workers, that can potentially put a Docker file in the right place that connects to it, that has all your packages precompiled, potentially uses package compiler to do all of this for you, and makes sure that when you're connecting to multiple nodes, that the SSH connections between all of these nodes are robust and easy to use. So this is kind of all infrastructural level things that can be a little bit challenging to do. And it's the reason for all of our work at Julia Computing and making this as easy to use with Julia Hub, which we'll jump to in just a moment after our next break. And so we'll show how that works and makes connecting to multiple machines a little bit easier to completely avoid debugging those SSH connection failures. If you're having trouble with that, that's kind of that's going to be unique to your exact systems that you're using and how you connect to them and how you spin up their machines. It's a little bit hard from, in an introductory course to go over all those details. But we'll show how it works with Julia Hub and some, so that's how this all can come together. So this is, the basics of getting this. There are other ways of structuring and sharing data between processes. One such way is the shared array, which I'm actually going to skip entirely because I really don't encourage you to use this anymore. In fact, I should delete this section on shared arrays because they only work if all your workers are on the same physical machine. And the way that they work is that they have all shared access to the same hard drive. They have all shared access to the same operating system, and so you can use some special structures there, but it's not going to scale to many workers across many nodes, across many boxes. And really, it exposes the same sorts of paradigms that threads exposes, right? The shared array gives you shared processing amongst multiple shared memory locations, essentially, across multiple processes. That's very much like multi-threading. And if you're going to do that, you might as well just use multi-threading. So I'm going to skip this section, both in interest of time and really because I don't know that I would recommend using it. I think it's nice to know that this package exists and it will do shared memory locations amongst processes within the same computer. But it's not something that you'll end up using significantly. We show how to do the same kind of prefix scan using shared arrays here and doing that pretty straightforwardly. Distributed arrays, however, are a much more interesting example. And just like we had done before, had talked about before, you want to using distributed to bring in our package, and everywhere using distributed to make sure all of our nodes are also using that distributed package. Same thing with the distributed arrays package. You load this in first on your master node to make sure that it's precompiled because we're all on the same file system right now. And then everywhere using distributed arrays to make sure to load it on all of your processes that are running. And now we have access to this really cool data structure that splits apart our data and makes it live across multiple processes. And so this special D-array structure, what it does is, let me make my screen a little bit bigger here, is it splits apart my matrix. So I have a 24 by 24 matrix. It splits it into 6 sections where the data for the top left here is stored on process number 2. The data for the bottom left section is stored in process number 3, and so on and so forth. And so I've split apart my data such that each process only has a small view into the data itself, which is kind of cool because now potentially these processes are living on separate computers, each of which have its own memory. And so I can potentially now have a single data structure that is bigger than memory, right? I can have a single data structure here that spans more memory than a single machine because each machine only has a small quadrant of it. And I can actually explicitly say how I want this to be set up. By default, it'll just do it in quadrants like this. And the size that I put here will set this up. And my initializer simply says how I want to initialize each local portion of my array. This is really cool. And even though our data lives on different processes, I should not say processor, but process number 1. This process number 1, none of this data lives on my master node. It all lives on my 6 workers that I have. But I can dynamically fetch any one of these values. And by indexing into my matrix A, so if I index into my matrix A at my first row, first column, I get a value back. And what's happening here behind the scenes is that my master node is seeing where does this value live, who has access to it, which process do I need to talk to, and goes and asks process number 2, hey, can you give me the value that you have at this location? And it will happily do that for me. And of course, it just gives me its ID because that's how I've initialized this array. So we can actually benchmark this, and it's kind of cool. You can do this benchmarking on other nodes too. So I can spawn at node 2 a benchmark to ask for what, how long does it take to grab that first value? It'll look and see where that first value lives, discover that it lives on node 2 itself, and can return the value relatively quickly. If I look at the last value, so a of end comma end, that's going to live on a different node. It's going to live on node number 6. And so to benchmark that, it's going to take longer because now every time that it accesses it, it needs to communicate with node 6, and it's going to have that incur a communication overhead to access this thing. So a question about, how by default it split this up. Why didn't it split it into columns, and instead it split it into, 6 regions where, so I have this A array here that is split into 6 different regions, and the columns aren't contiguous. Why would I want to do that? Well, there's 2 answers here. One is I can explicitly say how I want to initialize this, and in the help, it'll happily tell you how you can pass a distribution of how many chunks per dimension there should be. So for example, I could change this initialization so that way I have 1 chunk along each column and 6 chunks this direction. And oops, I think I need to pass this as a, wait, where is that? How did I do this? Dist is an integer. Oh, it's a vector, not a tuple. 1,6 like this. So I can say that, each column should be contiguous, and I'll split the columns 6 ways, and it'll happily put my my values this way, and split them up this way. Or the way, I forget how this exactly works, but it's totally configurable. You can choose which way, how you want these things. And so you can maintain common columns across workers. The reason by default that it does it this way, though, is because one of the main reasons for being for distributed arrays is for windowing functions. Because the way that you want to do compute here is, you want some algorithm that is fast to compute in your local regions, right? And so what I want to do here is I want to think about my algorithms in ways that I can, do all of my compute in a region at one time, and do some computation within, node 2 at once, within node 3 at once, do these things separately. And an awesome computation for this to work this way is to do like a convolution or some sort of kernel notebook where, if I'm looking at a given element and I want to look at its neighbors, then, I can do this and iterate over all of my, scan this convolution across my local portion very, very rapidly, because all of these accesses to get all of these nearest neighbors here are mostly on my same worker. It only gets tricky once I get to my edge point here. So if I'm, doing some 3x3 convolution at an edge point, well, then this one convolution, it needs to access worker number 2 to get its nearest neighbors. But far and away, most of my accesses are actually entirely local to each local part. And so I can structure my computation so that way each local worker, can do its, fast, 3x3 grid entirely locally without needing to incur any communication overhead, do its local regions. And so this kind of convolution is a very, very common task for distributed arrays. And so that's why we didn't get contiguous columns by default, is because it's not really thinking in terms of column access, but it's thinking in terms of convolutions or for like image processing or things along those lines. So you could, explicitly say that you wanted to configure this contiguously, but you don't need to. So as a fun example here, we can run the game of life. The game of life is a really fun little game. If you're familiar with it, this will be interesting. If you're not familiar with it, that's just fine. The way that this game works is that you look at the nearest neighbors. It's essentially a convolution operation where you just look at the neighboring cells to determine whether the current cell here should be on or off. That's that 3x3 grid that I was just drawing around. And so if we want to look at this, each local portion, all it needs to do is look at its local portion and then grab the outside edges from its neighbors. And so because this is all just done through indexing, we can grab data from other processes and get our data from the other processes just by indexing into our distributed array, padding out our local portion so that way each access can compute it and run our life rule. We can actually visualize this really kind of fun in a nice way, where you can use the colors package to visualize these as grayscale colors, and they'll actually show up as plots. Let's see if I have using images loaded, I think. If I have images loaded on my master node, I only need to load it on my master node because it's just for my own visualization here. Let's see if I can get this game of life going. This is just kind of a fun little example of running the game of life in a distributed fashion across all 6 of my workers. And let's see if I can visualize this now. Why is this not popping up my plots pane? That is working. Images of type gray. Oh, maybe it's because it's a Boolean. Sorry about this. Did I close my plots pane maybe? I don't know why that's not working. Bummer. I'm sorry about this. This is a fun little demo. Maybe it's working on your machines. I don't know why it's not displaying on my machine. Oh, maybe it's because I don't have ImageMagick in my current. Oh, it's because I didn't ever said using images. That's why. It's because the VS Code is trying to use images to display the package, but I don't have it loaded. And so then it's not going to display it. So the key thing here was to do the PKG add images and ImageMagick like we had done. For those of you who were with us last week, this is how we did image viewing. And then using images, we'll bring it in. And then I think this should work. Shucks, I should have had this pre-compiled. I had forgotten that I needed to display this in order to drive this point home. But this is the last point on our lecture on distributed compute, and then we can dive into GPU compute next, and doing it all on Julia Hub as well. And then we'll talk about distributed jobs in addition to GPUs, and doing them in the cloud, and how Julia works for cloud computation. So I think that'll wrap up this. Hopefully we can get this going. The last few sections on this distributed compute I can talk over while I'm compiling images here. But as we've noted before, you can actually connect to machines just directly with SSH. It's a little tricky infrastructurally to wire these things all up, make sure that they all have the same state, make sure that they're all working nicely. And so there's a bunch of ways of connecting to clusters. We have Julia Run, which is what powers Julia Hub now, which is built on top of Kubernetes, which manages Docker images and gets them all set up. But then if you also have other cluster managers, if you interface with on-prem clusters like Slurm or MPI or other ways of communication, they're supported as well. You can use the cluster managers package, which is linked here. The depth here is it's extraordinarily deep. And so in an introductory course, and the number of permutations of cluster managers is just nearly infinite. And so it's impossible for us to go over all of them. And the ways in which on-prem clusters are configured can be rather idiosyncratic. So I just point you to how these things work now, and the way that you can play with them. So to wrap things up, and then we'll see if we can get our game of life running. Multi-process parallelism really is the heavy-duty workhorse of cluster compute, right? It can tackle very large problems, including problems that are potentially bigger than memory, distribute them across a very large number of workers. Each worker can potentially have multiple threads, and each worker can potentially even have GPUs. And so it kind of all three of these distributed compute paradigms layer on top of each other and can all work in a heterogeneous compute environment. The key things to remember with distributed compute is that each worker is completely independent and has its own state. You must explicitly move data to them. You must explicitly move code to them. The plus side of this is that each worker is completely independent, and so you don't have accidental memory mutation race conditions like we had with multi-threading. So you can structure your algorithms to use a distributed mechanism that fits with that communication overhead game that we talked about, right? You want to use @distributed for parallel map reduce sorts of operations. And you can even have relatively small and fast inner loops because each worker will do their own for loop and computer intermediate reduction and only send one value back. PMAP is good for expensive inner loops that return where you want each loop to return a single value, right? Just like map reduces a value. Shared arrays are very much like multi-threading, which is why we skipped them in interest of time. And distributed arrays turn our problem on its head where we let the data drive where computation happens instead of vice versa. And so let's see if we can actually visualize our game of life now. And no, it's not working. Let's see, I think I need to do gray of array. There we go. Oh man, now I need to compile my image creation thing. Well, that's happening. I want to encourage all of you to head over to Julia Hub before our last break, and we are going to spin up a bunch of workers. Now, we're not actually going to go to Julia Hub. We're going to go to a special internal system that we have set up for all of us. It's dev.juliacomputing.io. You need to go to the HTTPS version of it, and you can just click the link that I put in chat here. You should be able to sign in with the way that you told me how you were connecting into Julia Hub. We set this up so that way it is the set up for you. And this gets to our secret sauce in development Julia Hub version. It looks a lot like Julia Hub, right? But it has this additional tab here that allows us to spin up VS Code in the cloud. So I'm going to ask everybody to go in here, log in, and click this launch button. Now, when you click this launch button, you need to change two things, or three things, sorry. We want to launch a GPU instance. And so you can choose exactly how you want to launch this application, essentially what workers in the cloud we want to spin up in order to run our code. And we want to use a GPU worker. We're going to use these K80 GPUs. So K80s are a slightly older GPU. V100s are the new hotness, but they're expensive. K80s are a nice way of doing a sandbox environment where we can explore what GPUs have to offer nicely and easily. So we're going to use K80s. So you click GPU tab, K80s, just one node. 2-hour time limit is fine. And then you need to enter, just pick some password, something that's easy for you to remember. This will be how you interface with your instance that you're going to launch. And this is the only tricky thing here. So I'm gonna, before I click start here, I'm gonna walk you all through that again, just because I want to make sure everybody does this. So the key thing, dev.juliacomputing.io to get to our secret sauce Julia Hub development version. Go to this URL, log in, and hopefully you'll be able to log in. If you have trouble logging in, let me know. You should be able to see an applications tab. And then, oh man, everybody's. All right, so those of you who are having trouble logging in, let's see, is there a common thing? I guess, are you logging in with a, shucks. So the 4 of you having difficulty logging in, did you do email password login mechanism? Gotcha. Okay. Shoot. I didn't realize that that would be a problem. I was thinking. So those of you that used open authentication should work. Those of you that used email and password, I didn't realize that that wouldn't work. Yes, that's the problem. Yeah. Shucks. We'll see if we can get that enabled for those of you who did that. I'm sorry, I should have realized. This is the first time we're trying this, so we'll see how this works. Yes, the email password method is those are the ones that are having difficulty. I'm sorry, I should have seen that coming. So those of you who can log in, let's start up your VS Code server because it'll take a few minutes to connect to it. So you go to the Applications tab, click the Launch button under VS Code Server. You should see Code Server as a default application here. Click Launch. We want a GPU instance, the default K80 node, the default 1 node. A 2-hour time limit is just fine. And now this password that you enter here, it doesn't need to be, it's just some password that you will use when you log into your code server. It doesn't need to be a very secure password. It can be whatever you want it to be, and you just need to remember it for as long as we start up your instance and connect to it. So that's this, and then I'm going to hit start. This will take just a few minutes to do, so that's why I want to do this now before before get us all started here rapidly. And then we'll see if we can get those of you with email passwords set up quickly. Yes, so then once you click launch, you'll start this application. And then once it's launched, you just click launch one time. Once it's launched, there's a connect button that will appear. If you try to do it too soon, it's not going to show up yet, right? We're spinning up a machine in the cloud, starting a VS Code server, and we'll connect to it. It's going to refresh this page. It'll take a few minutes to get started here, so that way we can look into GPU compute. Hopefully we can get this going. We'll see. This is a little bit of a risky thing. This is brand new stuff that we're just doing on our own side. We'll eventually roll this out to Julia Hub proper. The ability to connect to GPU machines, VS Code in the cloud with everything set up, and the ability to spin off distributed compute, multi-threading compute, and GPU compute all together, kind of to wrap this course back up together. So there, after a few minutes now, I've spun up my computer in the cloud. I get a welcome to code server, and then your password goes in here, the one that you just defined ad hoc when you spun this up, and it'll spin up a VS Code instance. So those of you who used email and password authentication, my apologies. We'll see if we can get a way around for you so that way you can play with this. Hopefully we can start playing with this. we can, yeah, we'll see how this goes. So yeah, if you see that application endpoint is not ready, just give it a second or two, and eventually it should load in. You're just waiting for the machine to boot in the cloud. So you can see that mine booted in the cloud. And now I actually have VS Code in my web browser. This is a fully featured VS Code editor interface, works exactly the same as the VS Code on my desktop. But now the beautiful thing here is that it's running on cloud compute. It's not running on my local desktop, and it's running on a machine that has access to a GPU. So while you all are getting set up there, I'm just going to jump back to my local instance, and let's see if we can actually play this game of life now. Yeah, I'm doing something funny here. So the problem is that I just don't have the display infrastructure set up. That's very frustrating. Do RGBs. Yeah. Yeah, I don't know why that's not displaying for me. It should display. Sorry about that. So we don't get to play the game of life distributedly. I mean, we do. It's doing its computation. It's just we can't visualize it nicely here, unfortunately. Frustrated about that. But we'll see. Yeah, I don't know why that is. And it looks like I just got a ping from our backend engineer. He says that we've run out of IP addresses. So some of us it'll work, some of us it won't. This is trial by fire here. Sorry that it's not entirely robust yet. We're working on it. So yeah, some of you won't get full applications. Bummer. All right, well, that's all right. We'll take a look at how this looks. You all can follow along on my screen. I apologize that we can't get this going in the cloud. This was kind of we knew that this was going to be a little bit risky, but the payoff would be that you could play with GPU machines. So hopefully some of you can. We'll see. This is still, in development stuff. We thought it would be fun to try it out with you all. It's a good test for our own network, and it's why I didn't do this until the very, very end here, because I knew it was a risky thing to do. So what I'm going to do is I'm going to jump over fortunately, I was able to spin up my node. I got lucky. I think maybe I was the first one that did it, and so I got in. So this is now in my browser. I'm connected to a remote machine. This is now a GPU. So I'll put this 080 GPUs.jl. This is going to be my notebook, my GPU's notebook that gives me access to GPU compute. So I've created this file here in the cloud that has the things that I want to run. So what is a GPU? How do we think about it? How do we work with these things? Well, the answer is let's dive back to my presentation here. Those of you can keep playing around with Julia Hub if you want as I talk about this. Maybe some of you will get in some more. We can see, yeah, we can see what happens. But yes, so how do GPUs work? What's going on here? Well, GPUs are kind of like SIMD on steroids. And they're kind of also like a remote machine that you connect to that can do SIMD on steroids. So inside of a machine that has a GPU connected to it, it has its own memory, it has its own processors, and they're geared for doing lots and lots and lots of parallel compute. So, we looked at what, for example, a traditional CPU looked like, right? That 4-core CPU had lots of dedicated compute for each core, lots of transistors dedicated to each core, lots of optimizations thrown at each core, so that way each core had become beefy enough that it could actually support multitasking or hyper-threading, where you can have 2 threads on a single core at the same time because there's so much architecture there, so much infrastructure there. GPUs are kind of the opposite. They're the bare bones processing units and the smallest processing units you can have. So that way you can have hundreds and thousands of processing units all together at once. So on my screen here, on the left here, is an image of a GPU. This is, again, a slightly old GPU. I like these visuals just because they're nice ways of visually understanding the difference between these sorts of things. So here you can see there are the 15 of these yellow blocks here that kind of look like they're these all 15 of these blocks are the same. And so if you were just to translate what you've known, what you've seen about CPUs and that image that I displayed of a CPU, you might think that this GPU has 15 processors, right? You might think, oh yes, this is 15 processors. That'd be a good guess. That'd be a reasonable thing to think, and 15-fold parallelism would be nice to have. But actually, each one of these yellow blocks is what's called a symmetric multiprocessor. And each symmetric multiprocessor has lots and lots and lots of compute units in it. In fact, so many compute units that you don't really reference a single compute unit by itself. You reference them in terms of what are called warps. And a warp is a group of 32 threads that are done in parallel and are kind of like SIMD. And you can kind of use the same sorts of thinking about, if you have 32 threads at a time, you can do 32 things at a time on all 32 threads at a time. And each one of these 15 symmetric multiprocessor has on the order of, I think in this particular case, it has on the order of 100 or so warps available to each one, which means that this particular thing has on the order of 2,000 compute threads that it could do, which is just absolutely mind-blowing, right? We've been talking about 8-way parallelism, 16-way parallelism. Here, suddenly we're talking about 2,000-fold parallelism. And this is an old card here. This is a very, very old card that is, representative of what GPUs looked like about 8 years ago. The concepts are all the same, though. The ideas are all the same. It's just things have gotten even crazier and with more and more threads. So there are so many threads here that we refer to them in groups, and the groups are called warps because of the second image that I have here. This is a loom, and the terminology comes from weaving, where the warp are the vertical threads on a loom. The weft is what you call the horizontal threads. And when you're weaving, you throw the weft through all 32 warps at a time, right? And you kind of weave through 32. If you have 32 vertical threads here, you weave through all 32 at a time. So that's pretty cool, right? I just kind of like the etymology there of where warp comes from. It's the vertical threads in a loom. And you can kind of use the same imagery here, the thread and loom and weaving kind of imagery. And it's like SIMD, except that it supports branching. That's where the steroids comes on, where if you have a branch, where we had talked about SIMD yesterday, that you have to do exactly the same computation on all of the lanes in your SIMD unit on a traditional processor. In a GPU, you're going to actually have a branch and do some computations on some threads and some computations on other threads, and it makes it far more capable. There's other ways in which it's more capable than traditional SIMD too, but this is one of the most salient ways. So if you have a group of, say, 8 threads coming in, a portion of your warp all coming in, and you have some branch, you're doing the single instruction, multiple data on all 8 threads at once. You branch, and if you look at the first 4 threads, say, and you do something for these 4 threads, well, all the others stop their computation. You do operations A and B, and then you switch and do operations X and Y, and then you reconverge and do all your operations in single instruction, multiple data form again. And so this is how GPUs can support lots and lots and lots of computation. They can support individual thread access, but in doing so, you're preventing all the other threads, all the other data lines from having things happening to them, right? And so you want to vectorize or think about your data in terms of groups of 32, or these groups, these warps of threads together in single blocks, and try to jam together as much single instruction as you can on these 32 threads at once. So that is the core, the crux of GPUs. And the key concept here is that we do the same sort of distributed processing as what we've done before. To move data to your GPU, you say CU, or this CU function will move it to a CUDA device. And so you can create an array on your CPU. This CU function will move it to your device, and it changes its type. And then it'll actually display by sending the data back to you again. And so this is how you can move data back and forth. And it's the same kind of almost distributed like compute, right? You kind of have a mini computer inside your computer that is dedicated for lots of parallel programming. And so this is how you can do it. There's lots of details here. But let's jump in and look at how this works and how it behaves if I have a GPU processor available to me. So let's see, I have a message. So those of you who are stuck, waiting for the application to start, if you've launched your application, tried to connect, and when you hit connect, you're stuck waiting for the application to start. If you can click this stop button to cancel things out and then relaunch, go through the same steps again, that should get you in. So those of you who didn't use email authentication and actually got logged into our system here, this is a good learning session for us. Those of you who did that, if you can stop and relaunch and reconnect, then hopefully you'll get in a few minutes here and can join us all on your GPU machines. But I'll keep charging ahead as you all play with that. So here, the first comments in this notebook just kind of talk about these distinctions, about how these are. And so the way that this all works out is, I'm sorry, I was wrong about my number of warps per multiprocessor. The card that I was displaying here has 6 warps per multiprocessor with 32 threads each. So that means that we have a total of 6 times 32 times 15 gives you nearly 3,000 threads at a time. The challenge is that each thread or each compute unit here is so anemic that it's actually hard to use all 3,000 of these threads at once. In general, you end up using less than the total possible theoretical maximum number of threads, just because you need to share resources amongst your warps and things like that. So each thread is relatively limited, but you can think of it as a SIMD unit that supports branching. So now that we're all on Linux devices, we can actually run Linux commands here. You can launch a Julia REPL and run, there's a command here. We're using NVIDIA's GPU stack, which is a CUDA GPU stack. So there's a command from the command line called NVIDIA SMI that can kind of inspect what is available to us here. So we have a single Tesla K80 GPU available to us. You can see how much memory is available on board, about 12 gigabytes of memory, how much is currently being used, how much, if its fan is on, a little bit about the processes that are connected to it and how much each process is using. And right now we don't have any processes connected to our GPU because we've not spun up our GPU stack on Julia yet. So how do I make use of this fancy compute device in my Julia session here? Well, a great example is from deep learning. We can, use a bunch of, let's see, how do I want to do this? Yeah, let's just run all this. This will take a little bit. Oh, whoops, I need to add Flux and CUDA here. So one of the challenges in getting this set up is that I need to install all my packages because we started from a blank slate. When we loaded our remote machine here, we started from a blank slate. So the work that I just did to test this out didn't propagate through. We're working on ways in which we add persistence here. But for now, this will just use a blank slate. So we can load up Flux. This will take just a moment to load up and use a deep learning example to see how this looks like on the CPU and compare it to how it looks like on a GPU. So I'm going to load up a train set, a test set for those of you who are with us on our machine learning examples. This should look familiar. We're building a chain of neural networks. And this is kind of the bare bones basics of doing a convolutional neural network on our CPU. So this will take some time to load up Flux, precompile it, load in the data, get it running. So I just executed all of those things. And we can then time how long it takes to run our program on the CPU. So give this just a moment to compile and get things going. While it's doing that, so this will be our concrete example of how to do, how to get this started. Oh, it's doing that. I'm going to load up a second Julia REPL here that allows me to, play along simultaneously while I'm doing this. So you have a Julia REPL. This is the REPL that's connected to my editor here. I can go into my other editor here and pull in CUDA and compile that and get this going. So that way we can do a little bit of parallel processing by hand here, right? This is the old-fashioned way of parallel processing. So I have one Julia session compiling Flux, another one compiling CUDA, and do this manually here. All right, while that's running, we're going to talk a little bit about how we work with GPU processes, right? So our data here, the way that we've set up this entire machine learning framework is all on our processor, right? There's no fancy GPU things happening. So we're just using regular old bog standard Julia serial processing to do this machine learning framework. And this is just how it would work on our CPU. And we're just using regular old floating point arrays, right? We're setting these up with floating point arrays. You can go in and look at what each one of these things are. Our model is all set up on floating point values here. And then we have our values here. To get it onto a GPU, I don't need this fix up script anymore because this has been fixed. We just need to use this GPU function, which is exposed by Flux, to move our data to the remote machine. This GPU function moves our data over to our GPU. It's kind of like sending it to a remote machine, right? We're sending it to the memory of our GPU, so that way we can do our computation there. And Julia knows that, hey, if the memory is stored on a GPU, we should do its compute on the GPU as well. And so all we need to do in order to move our compute there is to move our training data, our model, and the test data over to the GPU with this GPU function. If you don't have a GPU on your machine, this will be a no-op. It'll just say, hey, I don't have a GPU to send it to. We'll run this on our local machines. So let's peek back in on our our REPL here, and we are getting things set up, getting CUDA installed. It's getting there, almost there. Let's see here. And we have CUDA installed here. So now in this terminal, I can look a little bit about how this looks like while we're doing the comprehensive example and seeing kind of how the CUDA array structure works. So of course I can create a random array of 100 elements, right? And that's a standard Julia array stored in standard computer memory. If I use the CU function here or the GPU function, this will move that data set onto my GPU device. So Vish, if you're still having trouble, try stopping it and starting it again, and we'll see if that can get past that application endpoint. Well, we'll see. So here you can see that the type of my array here, so using the CUDA library, the type of my array has changed from a standard array to a CU array. It changed from a float 64. We've lost some precision here. The CUDA package is a little opinionated in thinking that 7 decimal digits is plenty, and so it'll automatically drop precision. And in doing so, it'll gain performance. Again, kind of like your SIMD units are, by dropping your precision, you can often get twice the performance, and sometimes even more so, simply because GPUs are really geared towards lower precision processing. And in machine learning kinds of applications where they really thrive, you'll see really significant improvements and without much change in the output, just because of the way neural networks work. So then when we print this out, it's a little funny. It prints out like a normal array, but you have to think about what's happening here is in order to print out each single element here, it's actually asking the GPU to send this to my CPU to process it, to send it to the screen so it can print out like this, and it prints from the CPU then. And so there's some communication automatically happening in the back end that isn't obvious and kind of obscures the fact that this is actually happening on a GPU. It looks like it's available to me to access directly, but it's here happening on the GPU. So let's go back to my editor here, and we can look a little bit about how might we rewrite a Monte Carlo Pi example in terms of GPU processing, right? So we had this Monte Carlo Pi example from earlier in the day called Serial Pi here that just takes a certain number of throws, right, and generates a lot of random numbers and gives me an estimate for pi. So a few throws, you get a poor estimate and so on and so forth. So if I wanted to express this using GPU processing, well, how would I do that? Well, the key is I want to express it in terms of warps, right? I don't want to grab single random elements. I want to grab lots of random elements. And perhaps one of the easiest ways to do that is by asking for CUDA arrays. So for CUDA, oops, I want to use CUDA.curand. So the interface here just changed a little bit. We want to use CUDA.curand in order to grab directly a random crand. Where is that? Oh man. The API changed on me here. Dang it. All right, we'll do it a different way. So we generate a random array and we move it to our CU. This is the easier way of doing it. It takes a little bit more processing, but it's just as easy. So we create an array on our CPU, send it to our GPU. Then we use broadcast to get this going. So this will do find pi on GPU with a certain number of elements, just like before. This actually does the computation on GPUs. And it's pretty cool, the way that this works. So what we're doing here is we're generating an array on our CPUs. We send it to our GPUs. There is a way to get this to do it in one step, just to ask for the CUDA to do this. And then we do this. The first time you do it, it takes a moment because it's actually compiling a GPU kernel for you. The second time you do it, it's extraordinarily fast and far faster than our Serial Pi example. So we can time this and ask for a relatively large, so say 10 million throws. You can do that and compare that to our serial version. Find Pi serial. What did I call that? Serial Pi. And ask for its timing. The GPU version should be faster if I reduced the memory usage here. So my problem here is that I'm not using CU-RAND properly. Problem with doing these fancy examples at the end of the day is my brain gets fried after 4 hours of teaching. So let's pull up the CUDA package. So CUDA.jl, this is where you can find all the great documentation for the GPU programming stack documentation. Let me just search for CU-RAND. They've been doing a huge amount of work on getting the GPU documentation and CPU, all of this working properly and integrating it into the base library much more, much more cohesively than it ever has been before. And so instead of having a separate function, it just has a separate RNG element here. Let me change that and fix that. This is where I was going wrong. So instead of asking my CPU to generate this random value, I can just ask to generate it directly on my GPU like this. And let's redefine this, and hopefully we can see a speed up then. Again, the first time we do it, it'll take some time to compile it. There's the speed up that I was looking for. Okay, so what I did here is instead of creating my arrays on my CPU, then sending them to my GPU, and then doing my computation, I directly ask my GPU to create an array of the appropriate size. And then by using broadcast dots here, the magic is that this will automatically create a GPU kernel that will work in terms of warps, do all the GPU programming magic that you need to do in order to do this. And this is kind of backwards of normal Julia processing, where normally we had talked about reducing allocations, reducing temporary scratch work. Well, here we're creating 2 temporary scratch random arrays that have our number of values in it directly on our GPU. But in doing so, we're able to express the rest of our computation in terms of a fused broadcast loop that can compile down onto our GPU. And instead of expressing this as a for loop, we express it as an array vectorized computation that then can give us the same answer, but with significantly faster, right? Whereas, so just to remind us, our find pi serial here, Serial Pi, took about 1/10 of a second. This was on the order of, what is that, 50 times faster. So you can really see just how big of an impact this is. Yeah, 26 times faster by moving to a GPU. And that's the kind of speed ups that you can often see if you can do this nicely. So let's go back to our REPL that's connected here, and let's see if we can get, oh man, this isn't working nicely for me. So using Flux. Yeah, there we go. Okay, I just didn't have this. Let's see if we can do this comprehensive example now that has a full-fledged, CPU training pipeline and then a full-fledged GPU training pipeline. And train. Oh, right. I need to do I did this incorrectly here. So flux.train. The Flux's API changed just slightly too here. So this will be updated in the notebooks in short order here for you all. Sorry about this. But the key thing here is that, we can set this up in a way that, just by saying GPU, by moving our data onto the GPU, we can, we're able to gain, again, it's the same concept. The data is on the GPU, and then therefore Julia will use that in order to do this. So I have the train function here not quite set up. So I have loss function. Yeah, so I need to pass in the params of my model. And then my data, my optimizer. That's the way I want to do it. But I need to define all this stuff. So let's see if I can get this working in time. Oh, M is my model. There we go. Okay, cool. So if you're doing a complicated Monte Carlo calculation with lots of for loops, I really think that you're going to have a hard time expressing it in a GPU computation, right? The only reason that I was able to express this Monte Carlo operation within terms of a GPU is because I could very concisely and easily, instead of working on scalar elements X and Y and squaring them, and it's a single, really it's just a single operation here, right, that I'm doing. And it's a single expression. Therefore, when I convert it into an array operation here, I can express it as a single array operation like this. And so I can use my dot squared notation. If you have anything more complicated than a simple sum like this, it's going to be really hard to express a Monte Carlo operation like this. And so instead, what you'll want to do is express it in terms of, I think Monte Carlo operations are the best in terms of distributed compute. And so you'd want to use your distributed compute chops there to split apart your task there and have them all come together. Yeah, that's a good question there. Man, I can't get this going. That's frustrating. I just don't have this updated. I'm so sorry about that. So, we can see this, way of building a GPU process. I have a more recently updated version here. And actually, why don't I just do that? So there's on my GitHub, let's do that, M. Bauman. And let's go to not this one, but the MNIST demo. This is exactly the example that we want here. So let me copy this and we'll. So I'm going to quick pull up an example that I know works because I've been iterating on it locally and working on it quite a bit. Yeah. All right. I'm sorry. We're out of time now, and this has been an exercise. So this has been a good learning exercise for us. Thanks for bearing with us on this GPU section. I'm sorry that not all of you got to spin up GPU machines to play around with these things. It's one of these things that's a little bit tricky to play with just because there's a lot of working parts and the GPU infrastructure really did just solidify around version 2.0, around the new CUDA package about a month ago. And I had forgotten about that coming into today's training. So that's where I'm running into difficulties today. we'll be working on this, and I'll send you updates. I know we're over time. So with that, I'll bring this session to a close. Thanks so much for all your attention and patience, especially with us for this last hour. Sorry that things didn't quite pan out the way I'd hoped, but hopefully, you'll you get a sense of the wide wide array of options here, right? We have multi-threading, SIMD, asynchronous tasks, distributed compute, and GPU compute. All 5 of these forms of parallelism work together, fully supported within Julia. Lots of ways of getting them going, and we're working on getting Julia Hub up and running with all of these forms of compute ready for you to use, and ready to use to spin up distributed jobs as well. So one of the things that we didn't have time to look at, but we can pull up here, is that you can actually spin up your own jobs and define clusters that spin up multiple nodes or multiple machines on demand in the cloud using Julia Hub. This is a lot of fun and really cool to see. And this takes care of connecting all of your machines together and allows you to spin up far more nodes, far more Julia processes than you have access to locally on your own computer. And so then you can go in here and play around with spinning up many nodes potentially of lots of processes. You can see how much this will cost, of how much these things will work potentially with GPU nodes. I have some cool videos demonstrating this. This is all new and exciting work that we've been doing. So I encourage you to check it out. I know we didn't quite get there to the end here, but need to work on consolidating in, or potentially maybe adding a 3rd day to this to really talk about cloud deployment. But we'll see how this goes. In terms of some of the questions that folks have, we can stick around. I'll stick around for an extra 5 or 10 minutes here to answer any questions. Y'all are free to go. Thanks for all your great engagement and questions. I hope to see you all around the Julia ecosystem. So again, julialang.org is the key central point for this, and the community tab is a great way to engage with the community, be it on GitHub, Discourse, Slack, Zulip, Stack Overflow, Twitter, YouTube, lots of ways of keying in. So I hope to see you all around working in parallel computation. Thanks everyone, and thanks for having this. And yeah, I'll continue iterating on these notebooks. Hopefully we'll get these up and running, we can maybe I can pester my architecture team and show you how this would work on Julia Hub in short order, sending you all an email or something like that to make up for the lost hour here. All right, take care, everyone. There was a few questions, though, that I want to answer. So anyone who wants to stick around is free to. The one question that I saw scroll by was on the maturity of the CUDA stack. So Julia GPU is kind of the center for the Julia stack. So juliagpu.org is where you can find, it's like the central interface for this. The GPU stack itself just hit version 2.0 recently, which brought a whole lot of stability to the API. And that's what I was struggling with in that last hour, was I didn't quite have my code up to date for the new 2.0 syntaxes. And the best supported platform is with those NVIDIA CUDA processing cards. So NVIDIA makes cards like the K80 or the Tesla V100. They all use this CUDA language that allows really easy integration with Julia, both using the high-level interfaces like Broadcast, just by moving data to your GPU and using Broadcast to do the element-wise instructions on whole threads at once. But you can also go into the CUDA stack and look at how you do, explicit CUDA programming. So there's some really cool examples here that you can look in to see, how you explicitly, do some very explicit CUDA programming, where you explicitly go in and talk about each warp independently. And so these warps have things like block indices, thread indices, and there's ways of essentially writing CUDA code. So if you've ever written C CUDA code, this will look very familiar to access the thread index, the block index, using the GPU's warped and symmetric multiprocessing design to give you the kinds of SIMD sorts of computation that you want to have. And so this is how you can do some sorts of really fancy, nice GPU computation and do these sorts of computations on the CUDA directly using, again, you use macros to introduce new keywords. So like the CUDA macro will define these functions on the GPU and things like that, and use GPU instructions. So this is the low level interface, but then there's the high level interface of just using Julia, pure Julia broadcasting code. And so that's very stable, really awesome. There's some experimental support for AMD GPUs. This is still new and a less trod path in general. And so, but it's coming along, lots of work being done there. And so this is how you can key into this. See if there's any other things. Yeah, I'll send. I'll add the slides that I went over to the GitHub repo and continue iterating on these training repos, so that way we can get these things for you all. There's a question about TPU processing, and I actually do have a slide on that here. And TPUs are kind of, you know, the next iteration of GPUs, where you can have lots of pods of these things, and you can rent these from Google. You can't actually buy a TPU. You have to rent cloud usage of them on Google. So it's a lot harder to display, and it's a lot harder to interface with in general, because it's a very constrained environment. But we actually have Julia working on these things. You can, just like you can move data to a GPU, you can move data to a TPU. The same sorts of infrastructure works there. It's a lot more limited in the instructions that have been defined, just because we don't have many folks using TPUs in production, whereas GPUs are used in production every day. Many hundreds, thousands of folks are using GPUs in production in Julia, and it's a much more full-featured stack. TPUs are a lot more idiosyncratic, but are indeed supported, and so there's some cool little tutorials on doing that. It's the same kind of concept as a remote computation device that can give you the promise of an answer in the future. So yeah, that's how you do this. If you have, yeah, so Tobias asks a good question about the Monte Carlo examples, and, you know, would you use the Julia built-in distributed package, or would you use a specific cluster manager? The answer there is simply dependent upon the hardware that you use. The actual Julia code that you use will be exactly the same regardless of which cluster manager you're using. You know, I would use the standard distributed package, and then if you're using you know, interfacing with an on-prem cluster, the kinds of cluster managers that you interface with the distributed package will be different, right? And the way that we have Julia Hub set up is that it, in the behind the scenes, without you ever knowing it, it actually uses Kubernetes to connect all of these things together to dynamically scale up pods, get you know, get all your workers connected together, but you're just using distributed Julia code. And so at an algorithmic level, theoretically, it shouldn't make a difference which cluster manager you're using. Now, that's not entirely true, because some of the cluster managers are far more opinionated about how they work, how they process code, how they send code around, and don't layer on top of the standard Julia distributed paradigm that we demoed today. And the key one there is MPI, is the one that you may run into. It's kind of the old workhorse of distributed compute. A lot of the same concepts apply, but they have their own idiosyncratic ways of doing it that don't key into distributed standard library quite as nicely. You have to use the MPI library directly when you're designing your algorithm. The choice there as to which one you use, though, that'll be driven by the hardware that you're running on. And so if you want to just run cloud computation easily and quickly without worrying about it and just spin up these things on demand, I encourage you to look into Julia Hub, where we're rolling this out. And you know, you saw a sneak peek of our development machine, which wasn't quite ready for real time for good reason, as you all discovered today. That's why we've not enabled that for everybody. This is kind of our trial by fire today, but yeah, so you can do that. You can actually spin up compute on Julia Hub proper, the non-dev version. And the one thing that we added was the availability of the VS Code in the browser on the dev version. That's what we were trying to do today. But the parallel compute on Julia Hub, that just uses the distributed standard library that allows you to connect to multiple workers that way. And then the actual algorithm you run, that's up to you. Any other questions about any of the things that we talked about today, be it GPU processing, distributed, or any of these other paradigms, right? We've covered a huge gamut that didn't just cover Julia itself, but also lots of how modern hardware works and the way that things work. So it's just kind of a reality of the world these days that we have such a huge heterogeneous environment. And in order to get the best performance out of this heterogeneous environment, we need to use heterogeneous sorts of strategies that all layer on top of each other and ideally all multiply together. And so a really fun example, just while we're sitting around, as long as folks are hanging around here, a really great example of all of these tasks leveraged together in a nice way is Jonathan Laurent AlphaZero package. And this is a package that implements a machine learning task that tries to learn a game through a combination of learning and search. And so it uses a neural network and it uses Monte Carlo tree search to try to narrow in on the number of possibilities that it should search when it's solving a game, to train a game solving agent. And this was the agent that notably beat a human at the game of Go back in 2016. Google initially developed this. And now there's lots of implementations that have taken the white paper that Google released as a result of that and implemented it. And this is the Julia implementation. And it requires a lot of compute, especially once you start talking about the more complicated games. And to really make the most use of it, this uses three of the strategies that we talked about. It uses distributed compute to split across the problem into multiple machines. On each machine, it uses multi-threading. And the way it uses multi-threading is a little interesting. It uses multi-threading to batch up jobs that it can then send to a GPU. And so remember, to really get a GPU job beefy enough to really crunch on, you need a lot of data to process at once in a way that you can work whole warps at a time. Well, then, the way this gathers that data up is by using multiple threads to put together a single data structure that you can send to the GPU to do GPU compute. And so this is a really cool example that mixes distributed compute, multi-threading, and GPU compute. And we actually had this running on Julia Hub, where you can spin up the workers on demand and have distributed compute, multi-threading, and GPU all interfacing together really nicely with Julia. So this is a fun thing, and it's pretty small, right? It's pure Julia code, so you can see how it works, and it uses the pure Julia distributed multi-threading and GPU libraries. So you can take a look at that. That's kind of a fun advanced case to look into. So the way that I shared data across workers was simply by asking the distributed macro when it was kind of seamlessly done in the background, where in my distributed code, when I, let's go to, for example, my partial pi here, when I p-mapped this, the argument that I sent, the PMAP itself actually ended up sending out all of the data to the partial pi function to compute. And so this happens seamlessly, whether you're using PMAP. PMAP will automatically send the data to the workers, the arguments that you're passing here, it'll send that to the workers. If you're using, the distributed function, the data is actually incorporated inside this for loop. Any data that we reference actually gets sent along with the code as we send it and use it. And so this is one way of distributing data kind of in an ad hoc manner that happens behind the scenes without you even realizing that it happened. Of course, in order for partial pi to compute its result here, it needs to know what values, which range to run on. That's the data that we sent to the worker. And so in this case, it's a very small data transfer, but it's data transfer nonetheless. If you have bigger data sets, really the way that I encourage you to work with it is to access the data directly. And so split your job apart at a higher level, so that way you split on, say, S3 bucket names or S3 objects in a bucket, where each worker would just, you would send the data that you send to the worker is just the name of the object that it's going to process. And then the worker itself will reach out to S3, download the data locally to itself. So that way the master node doesn't need to process or hold on to all the data itself, right? That could be intractable. And so instead you just send the workers a pointer to where they're going to get their data, and then they can download the data themselves and process it. And then of course, that's a wholly independent step. So could you use distributed array to maintain a distributed database? Well, the distributed array object isn't really made for serialization. I don't know that you would be able to make that persistent in any way. I think that it kind of holds on to which nodes are using it just in memory in a way that's not serializable, if I remember right. So it's not going to be a persistent database in any case. You could do it, yeah, you could use the same sort of structure though. It's actually a pretty simple structure, and you could mirror that. And I think I would try to do it in a way that's a little bit more tailored to your use case. But you could follow the same sorts of things. Again, just as always, right, distributed arrays is itself a Julia package that you can dig into and see exactly how it's defined and how it works. And you can see how it keeps tabs on which portions have each, which workers have each portion and things like that, and how it communicates with its workers and such. And so, you can see which workers are here based on the processor IDs or process IDs. And, you could do something similar. It's pure Julia and just stands atop the distributed standard library to do its work. I think I would use, I would look to this for inspiration if you wanted to do something more full featured, but I don't know that I would use it directly. And yeah, then you could have, for example, ways in which you're, tag S3 objects that populate different portions of it, or have time indices, or do very specific sorts of things. And there's other ways that we're working on with Feather, and these things, Vish. You're on top of it. More advanced ways of interfacing with distributed data structures. Yeah. Right. So the concept that comes from distributed arrays that I think is a nice concept to have is the idea that you do this kind of compute agnostic sort of thing, where as a programmer, you don't need to worry about where the data lives, and you just have a single data structure that knows where it lives and then can run the compute in the proper place based upon who has it, as opposed to vice versa. That's the kind of fun mind game that distributed arrays plays, and you can extend that to other, to your own data structures too. Yeah, exactly. Time for a beer. Thank you all. Thanks for being a part of this. I'm going to sign off here. But yeah, hopefully sometime in the near future we can, meet up at a JuliaCon and share a beer if that's ever ever allowed again. Take care, everyone.
Bye.
Bye bye.